Okay. Good morning, everyone. Thank you to be here. This is the first workshop organized within the framework of an European proposal from the Marie Curie Action, which is called DryNet. DryNet is a kind of project which supports different groups working all worldwide, Europe and third countries, people from Japan and from Thailand. The aim of the action is just to establish a network, an international network, that brings together scientists from different disciplines. We have engineers, we have experts on biophysics, I guess. We have embryologists, we have cell biologists, we have molecular biologists, people expert on some models, just to see whether we can exploit some of the strategies that nature uses to survive without water. I don't know whether you are familiar with it, but there are some organisms which are called anaerobiontic organisms, which are able to withstand water deprivation, okay? Some of them are larvae, and when water goes away, because, they undergo desiccation, okay, and then once water comes, they enter a kind of state of dormancy, is called, like a diapause. Then water comes back again, and then they restart life. So there are two groups working in here from Italy. One is from Modern University. The second group is based in Japan. They focus on these models, tardigrades and midge cells. Midge is a kind of little fly. And all the rest of us are going to learn from these animal models to see whether we can use the same tricks for apply a kind of reversible drying in the cells and in gametes. Today's speakers are leading scientists in the fields. So we will start first from the guest, which is not part of the DryNet consortium, but is a preeminent scientist working in bioengineering, Professor Wim Wolkers from the University of Hannover in Germany, that will tell us about dry preservation of cell and tissues, application in regenerative and reproductive medicine, okay? So he works specifically on the membrane biology. Let's see what he's going to tell us. The second speaker for this morning is Professor Alberto Cincotti. He's from University of Cagliari. He's a partner of the DryNet project. And he's going to tell us, he's an engineer. He's an associate professor in engineering faculty in Cagliari University. And will tell us about mathematical modeling on living cell desiccation, the continuum engineering approach. That's the second talk. They are very specialistic talks. All the talks will be held in English, so it's going to be a free English lessons for you, girls, students. And the other speaker, which actually unforeseen, is not on the program, but it's just a new entry from yesterday night. We discussed it to have another speaker, which is a biophysicist, right? He's Professor Santiago Aparicio. He's a member of consortium from UBU, University of Burgos, and is a specialist of biophysics and interaction of some molecules, okay, and medium to protect the cells. The other speakers are actually local from Teramo University, part also for the DryNet, and are Dr. Marta Cernik, which will tell us about the late embryogenesis of abundant proteins and reversible drying in somatic cells. And the last speakers is a PhD student of my group. It's Luca Palazzese that will tell us about the rental potential of dry spermatozoa following intracytoplasmatic per injection. So I realize it's a very unfortunate period because, we wanted to organize that workshop earlier in April, but the project officer, which tomorrow will join us for the formal meeting, okay, pushed that to shift a bit in today. So we are very well aware. It's a very unfortunate moment because all the students are away for the bridge, because yesterday it was a public vacation. We will have another public vacation the 1st of May. Also, the students and the professor took the chance to desert the university. So that's really is a pity for us, a point of view, but what is most important here, just to exchange ideas between these scientists. I'm very curious to see the talks, okay, of course, mainly from the guest. And I will give the floor right now to Professor Wim Wolkers. Please take the floor for the talk, Dry Preservation of Cells and Tissues, application in regenerative reproduction medicine. We will go. Yeah.
Is it on? Okay. Okay, thank you for the introduction. I'm going to give a presentation about dry preservation of cells and tissues. I come from the University of Hanover. I'm in an engineering department, so the studies I do in collaboration with the veterinary school in Hanover or with Hanover Medical School. Today I will predominantly talk about a collaboration I do with studies with the veterinary school in Hanover. It's important to have collaboration partners to really move forward with this. So what will I, now I need to figure out how this works. I just, the smallest first. Just see that it's it is the point of it. Yes. Maybe you have to. I can do it by page because it's not there. Okay. The other way. Okay, then other direction. The other direction. Okay, as an outline, I will start with giving an introduction. Into an introduction, how do cryoprotective and lyoprotective agents work? What is their mode of action? I will predominantly talk about transport processes related to preservation, loading of protective agent in cells and also in tissues. So you need to think about the membrane permeability barrier and also diffusion of molecules in tissues. So that is the first thing you need to think about. Then I will talk about real-time freezing studies to study membrane phase behavior during freezing. And I will give a few examples at the end on some real-time projects that we are working on. If you have cells, mammalian cells or tissues, and you want to preserve them for longer periods of time, there are various options. The simplest way is hypothermic storage, is simply storing in the refrigerator. This does not give you a long-term survival. You can store things for about a week. Cryopreservation allows storage in liquid nitrogen, so that is minus 169 degrees Celsius. For prolonged storage of cells. Vitrification is actually the same as cryopreservation. It's also known as ice-free cryopreservation. Because if you have a cell in water, water will turn into ice, and ice creates problems. It's very damaging too. And vitrification is sort of a new method. Then the preferred method, and that's what this symposium is about, is actually dry preservation. So if you're able to store mammalian cells and tissues at room temperature in a dry state, of course you can imagine this has various practical advantages. One of the methods to do this is freeze drying. So if you want to go to freeze dry mammalian cells, the first thing you need to know is how does cryopreservation work. So I will also talk a lot about what happens during freezing. Because freeze drying is a combination of freezing and drying. If you don't understand this cryopreservation part, you're never going to achieve the freeze drying part. So why is freezing and drying, why is it so damaging? Well, if you have a cell in water, the first thing that will happen, if you, for example, if you cool a cell into water, ice will form. At the moment ice is formed, excuse me, the concentration of salts increases, and this creates an osmotic gradient, and as a reaction the cell will dehydrate. And this process is also dependent, I'm going to come back to this later, is also dependent on the cooling rate. So if you cool very fast, this does not happen, but in this case intercellular ice is formed. Also at the molecular level, so you have the cell as a whole which you have to consider, but also at the molecular levels, proteins tend to denature, unfold, they're not in their functional state anymore after freezing or drying. And if you think about the membrane, that's the most important barrier for a cell. A membrane undergoes phase changes, and these phase changes are very damaging because they lead to leakage of intercellular components and a loss of cell survival after thawing and or drying. Good. So drying is, freezing and drying are very damaging steps, so you need protective agents. And nature has actually found solutions to overcome freezing and drying stress. One of the things that I worked on as a PhD student is this resurrection plant. This is a plant that you can dry it, including its roots and leaves. You can do this with any plant if you don't give it water, of course, but the difference is that if you give water again to this plant, it revives and it resumes metabolisms within a day. So it's a very spectacular plant. You can find it, for example, in South Africa and Kenya, the resurrection plant. One of the things that, and there's also the tardigrades, it's a well-known anhydrobiotic organism, and their seeds and pollen in plants, which are even more adapted than these systems. One of the things that these organisms have in common is that they synthesize large amounts of protective agents. In this case, tardigrades synthesize trehalose, and this synthesizes sucrose in really high amounts. And this forms a so-called glassy state. This is a highly viscous state that sort of immobilizes the cell and its cellular components, so that there's no molecular motions and no degradation reaction takes place. And this allows the organism to survive drying. This is very simple. There's a lot more complex adaptative mechanisms that are also needed, including the synthesis of specific stress proteins. Okay, so these were a few examples of organisms that are able to naturally survive freezing and drying. But how does it work with a mammalian cell? A mammalian cell does not have mechanisms to survive drying and generally does not survive freezing or drying. There are a few compounds known that are able to protect cells during freezing. Cryoprotective agents, and well-known compounds are, for example, glycerol, ethylene glycol, and dimethyl sulfoxide. These are typically small molecules that permeate the membrane, and you can get them also inside cells, and they can be used, particularly glycerol, for sperm, and dimethyl sulfoxide, for example, for cryopreservation of stem cells. Nowadays these are routine procedure, but you have to be aware that not every cell type can be cryopreserved. So for each case you need to find specific conditions and specific types of cryoprotective agents. There's also a specific class of cryoprotective agents, sucrose and trehalose, and they are non-permeating. They're a little larger, which makes it difficult to get them inside cells. Okay. But they also can be used. And there's larger components that are also needed, osmotically inactive polymers and proteins. And usually you need a combination to cryopreserve or freeze dry the cell. How do they work? What all these compounds have in common is that they are actually preferentially excluded from the surface of membranes and proteins. So if you have a solution of a protein in water and you add the cryoprotective agents, they do not interact with the protein surface, they move away from it. And this stabilizes the native state of a protein also during freezing. This is known as the preferential exclusion theory, discovered by Arakawa and Timashev. This is also disaccharides, DMSO, have these mechanisms. They stabilize proteins and also membranes by moving away. If you go further, and that means if you think about freeze drying, then what, for example, sucrose is doing, it is able to replace water, because in this case you remove all the water, so also all the residual water. Sucrose is able to replace water during drying. And if you think about the membrane, so the membrane is the most important barrier for a cell. In the hydrated state, the membrane has a fluid phase, so the acyl chains, they look like this. So the acyl chains are freely moving. If you dry them without protective agents, the water around the phospholipid head groups here is being removed. And this causes the formation of gel phase because the acyl chains start to interact with each other by van der Waals interactions. This causes gel phase formation, and this is generally not good. If this happens, a lot of cells will die. This phase change, they don't like it because it leads to leakage. Trehalose and sucrose are able to replace this water by interacting with the phospholipid head groups and prevent this phase change. So they prevent leakage, and also during if you rehydrate again. Yeah, so this is particularly interesting for freeze drying, for dry preservation, that these molecules are able to do this. There's one extra thing, because a lot of molecules are able actually to do this, to interact with phospholipid head groups. This alone does not give protection. There's another thing you need, and that is vitrification, glass formation. You need to immobilize the system. Before I go to that, so glass formation, that's what I said, so you need to form this highly viscous state, and sucrose is able to do this, but not all components can do it. So it needs to be highly viscous so that you immobilize the cellular matrix. What is actually the difference between a cryoprotective and a lyoprotective agent? The difference you can actually visualize in a so-called state diagram, which is actually shows the effect of water on physical properties of a molecule. So if you think about, for example, glycerol. Glycerol is at room temperature. It's a fluid, right? So at room temperature, it is in a fluid state. Only at very low temperatures, minus 80 degrees Celsius, glycerol starts to vitrify and forms this highly viscous matrix. That's why glycerol can only be used for cryopreservation. On the other hand, sucrose, it is able to form this glassy state already at room temperature. So it forms this highly, as you may be aware, sucrose is in a solid state at room temperature. Unless you add water to sucrose, then it starts to dissolve. Water plasticizes this glassy state. So that is actually the difference between cryoprotective and a lyoprotective agents. So it is actually it is related to the glass transition temperature. So this is an important parameter for dry preservation. Okay, if you look at this, you would think, well, why don't you use sucrose for cryopreservation? Why is this not standard use? The reason for this, why sucrose is not standard use for example, cryopreservation of cells, has to do with the membrane permeability. And this shows a diagram of permeability of molecules, so membrane permeability. For example, here is membrane permeability of water. So membranes are relatively permeable for water. The water freely has fluxes in and out of a membrane. Glycerol is here. The MSO is probably a little in between glycerol and water. Sucrose, so disaccharides, are completely at the other side. So they hardly move, but are able to pass the membrane barrier. So this is a problem. If you want to cryopreserve or freeze dry a cell, you need to find a way to get it inside the cell, because otherwise it's not going to do anything. It's only outside the cell. So this is one of the challenges that we face. I will talk about it in the third part of my presentation. That's actually there are various ways to get it inside cells. So the challenge is one of the challenges to get cells, protective agents inside cells. So in this next part of my presentation, I'll talk about some studies we do on actually how we study permeability of cells to water and to various cryoprotective agents. So this is an important aspect that you need to study if you want to go towards freeze drying of cells. One of the first things that you need to know if you want to understand, if you want to design a cryopreservation protocol for a given cell type, is its osmotically inactive volume, and this is related to the membrane permeability of water. If you have a cell under isotonic conditions, so that is in a normal physiological buffer, it has a certain volume. If you add salt or sugars, so a non-permeating molecule to the medium, the cell starts to shrink. If you add water to the same solution, the cell starts to swell. And this phenomena can be described by the so-called Boyle-van 't Hoff equation, which is illustrated over here. And actually this is an experimental data set. So the volume, if you increase the osmolality, it shrinks or it swells dependent on medium osmolality. And the extrapolation of this curve gives you the VB, that is the osmotically inactive volume of the cell. And this is one of the important parameters you need to know. It's cell specific, and you need to know this if you want to, for example, model how to design a freeze-drying or cryopreservation protocol. So water permeability, the Boyle-van 't Hoff equation, can be studied using non-permeating molecules, sucrose, cellulose, sodium chlorides. So this is how you can study this. I also have a movie about how you can actually derive the membrane permeability of a cell. Now I'm going to need a little comparison. Okay. So a cell has a certain, this is an example of an oocyte, has a certain permeability for water, and this is an oocyte from a porcine oocyte that has been exposed to CPA solution, a DMSO solution, 5%. So what happens is, you will see, this is a micromanipulator, so it's to hold the oocyte in position, and we flush the oocyte with a DMSO solution. What happens is the first reaction of the cell, it starts to shrink, because the DMSO is not inside the cell, and water inside the oocyte will go out of the cell. But upon time, and this is a very long time, and I don't want to bore you too much with lengthy videos, but you will see that the oocyte, the volume starts to regain its normal volume again. And here you can see now at the end of the experiment, it almost has its normal volume again. So if you expose a cell to a cryoprotective agent solution, you have to do this very careful, because this can be damaging. The cell starts to react osmotically, and if you are not careful, the cell will already die at this point. From these experiments, now I have to go back to my presentation mode again. Yeah. What you can derive from these experiments is the cell volume. You can extract all these images, yes, I think good, and analyze them over time, and you can derive the relative volume over time, and that is actually plotted over here. This is for, what is this, an ethylene glycol solution. This is a DMSO solution. You can see the cell shrinks, and then it goes back to its normal volume again. For sucrose, you only see this one response. You can see that it only decreases in volume. It does not go back to its original volume, because the sucrose is not going inside the cell. From this response, we can actually derive two things. We can derive the permeability of a certain cell type for water. That's predominantly from the initial slope here, so the shrinkage of the cell. Because what I've shown in the initial curve, right? The permeability for water is relatively high, and that for a CPA is, compared to water, is going slower inside the cell. And the CPAs going in is actually occurring during the second phase. So from this complex response, you can derive the permeability to water and towards the CPA. We've actually derived these with various equations. I don't want to go into detail how you do this, but just to illustrate, this is how we collaborate. This is why the collaboration with the veterinary school works very good, because they have all the expertise, the micromanipulator system, and the oocyte handling, and we in our department do a lot of the calculations, the data analysis, so that works really good. So how to analyze these data, just to give you a brief flavor. So there's an equation that describes the water flux, so what I said, the shrinkage of a cell or the swelling of a cell, the water going in and out of the cell, and it's dependent on the cell properties and on the osmotic gradient in and outside the cell. And there's also a solute flux, so that is the cryoprotective agents that slowly goes inside the cell. These two equations you can use, you can fit the data with these two equations. Then there's a variety of other models that you can also use with it. Just to give you an idea how you can use these volume data to get really experimental parameters that can be used for cryopreservation modeling. This is a cell system. We are also interested in cryopreservation and freeze-dry of whole tissues. This is, of course, much more complex. Cryopreservation of cells is just a small system, right? You're thinking about 10, 20 micrometer, maybe if you think about sperm, it's a little smaller. Anyway, small systems. If you think about a tissue, of course, you go in the millimeter, centimeter scale. So that creates an extra challenge, and this challenge is diffusion. So you need to think about how do molecules, protective agents, diffuse into tissue. And these are things that we also study. We actually, because we also have an interest in cryopreservation of oocyte, of ovarian tissue, and later also in the medical field we also have an interest there. Good. So how can you study diffusion? Just to illustrate you how you can do that, you can, in case of this ovarian tissue, we just take biopsy punches and we incubate these biopsy punches of this ovarian tissue in CPA solution, and we keep them for a certain amount of time, for 30 minutes, for an hour, whole night, and then we transfer them to a PBS solution again to allow leakage of the amount of the CPAs that have been diffused into the tissue. It's actually a relatively simple method, so it allows you to find out how much cryoprotective agent has been diffused into the tissue. How you can measure this is with an osmometer. So if you have a lot of CPAs that are inside the tissues that have leaked out into your PBS solution, this will affect the freezing point of the solution. And so you can, it's a very simple, you don't need advanced instrumentation to measure this. You can simply measure the freezing point of the solution, and this will tell you how much of your CPA is in the solution, and as a function of time. We have done this for ovarian tissue, and actually the results are shown over here. So you can see that cryoprotective agents, we've done this for a variety for sucrose, DMSO, and a variety of other molecules, and you can see that over time the CPAs go into the tissues. And you can also, why is this interesting, you can see the time you need to do this. So you have to think about, it takes at least half an hour to an hour to fully diffuse a certain tissue of a certain dimension with your cryoprotective agent. So you need this information if you want to think about freezing or freeze drying a cell. These are fundamental things that you need to know before you start to work in this field. From this you can actually derive diffusion coefficients and actually calculate how CPAs are diffused within the tissue in various dimensions. And you can see that some CPAs go faster and others depends on the molecular size of the size of the molecules and the physical properties of the molecule. We also have another method, Fourier transform infrared spectroscopy. Just showing this, maybe this could be of interest to do some collaborations in this field. We have a new method here where we can look at permeation. I'm not sure if you're familiar with the technique. I'm not going to explain the technique in detail, but this is how it looks. So you have a measurement surface, a measurement crystal here, and you have your ovarian tissue here. You put your favorite solution on top so that you want to study, and you look at permeation through the tissue, and you can see, you can pick up an infrared spectra over time. Sucrose and DMSO, they all have specific characteristic bands, fingerprints in this spectra. And you can actually, why we use this technique? Because you can measure multiple components in a vitrification solution over time. So you can separately monitor ethylene glycol, the DMSO, sucrose, and whatnot, complex system. So with this method, we can actually separately look at the fusion of multiple components. There's very complex equations that you can actually use to fit the data and derive the fusion coefficients from this. Yeah, so this is something that we've recently worked on because if you think about cryopreservation and freeze drying, it's not going to be one component. You need to think about multiple components. It's not going to happen with one component. It's not a trivial thing to freeze dry a cell. So with this method we can actually study complex mixtures, look at the fusion of multiple components over time. And that makes it a very powerful tool. We've recently published this work in the Analyst. In the next part I want to talk a little bit about studies we did on membrane phase behavior during freezing. So really what happens during freezing in real time. And this, I will use this as the first step to go towards freeze drying a cell. If you want to freeze dry a cell, you first need to understand what happens during freezing. So I will talk a little bit about that, and then also see how we can even introduce disaccharides into cells and use this for cryopreservation. The first thing that you need to be aware of is that if you freeze a cell, the cooling rate is very important. So you also need to consider this if you freeze dry a cell, of course. Freeze drying, with a normal freeze drying system, you cannot control the cooling rate very well. But you need to use, an alternative method to cool your system. So how does the cooling rate affect cell survival? This has been described in the two-factor hypothesis by Peter Maser. If you have a cell in solution and you cool it slowly, extracellular ice will be formed. Salts will not participate in the ice. So as a consequence, you get a freeze-concentrated solution where you have ice, salts that are not in the ice phase, and some residual water. This creates an osmotic gradient, and this causes dehydration of the cell. This is not good. Cells don't like this, and this may result in cell death. If you freeze rapidly, if you increase the cooling rate, cells do not have enough time to respond osmotically to this osmotic gradient. So as a consequence, water stays inside the cells, and this water eventually turns into intercellular ice, and this is almost always lethal. So this is what you definitely want to avoid. So cells typically have an optimal cooling rate in between these damaging mechanisms where survival is maximal. This is an important axioma in cryobiology. We also need to use this if we go towards freeze drying, because we need this optimal cooling rate before we even start to think about freeze drying as well. So this is important. There's some recent studies where you use freeze drying. You actually are thinking about very high cooling rates. In this case, you avoid ice formation altogether. I'm not going to talk about it too much in detail, but you need very high concentration of cryoprotective agents and very high cooling rates, and you can avoid ice formation, and this also can be used to allow freezing survival. How can you study these phenomena? You can use, for example, cryomicroscopy, and these are things that where we've learned a lot from how cells behave during freezing. So what I said is intercellular ice formation. If you freeze too rapid, you can see it as what we call blackening, and it's referred to as blackening in the literature. So cells, they suddenly turn black, and this is an indication that intercellular ice is being formed. Also, if you have a cryomicroscope, so you need a special microscope for this that allows you to do studies at very low temperatures. You need to flush your sample to avoid condensation. That's the main issue, and be able to accurately control the cooling rate. You can also study the volume change of a cell from microscopic images and use that to derive water permeability of a cell at sub-zero temperatures. That can be done. I've used Fourier transform infrared spectroscopy a lot to study membrane phase behavior during freezing. It relies on molecular vibrations. So proteins, lipids in cells, they have a characteristic bands in an infrared spectra. And for example, you can study water turning into ice. So water has some very characteristic bands. They turn into ice. You can easily see this. There's also bands arising from membrane lipids and from proteins. We're particularly interested in membrane lipids. Very small bands, but if you do some data analysis, you can derive membrane phase behavior during freezing. And this is one of the most interesting things that we found out. At the moment, you get, if you have a cell in water, at the moment you freeze it, so you cool down the temperature. At the moment you get ice formation, you can easily trace that from the spectra. You can see that membranes, they undergo a phase change from the fluid phase to the gel phase. So ice formation, and this is related to this dehydrating effect of freezing. Ice formation induces a fluid phase change from fluid to gel phase of membranes. This is related to the removal of water from the phospholipid head groups. And you get the nice thing with FDR, you get infrared spectroscopy, you can study this in real time, this phenomena. We studied this for stellium sperm, for example, and you can see that this phenomena is dependent on the cooling rate, as I already explained, and also the ice nucleation temperature. So dependent on the ice nucleation temperature, you have this phase change or not to a lesser extent. You can actually analyze these kind of data to derive the membrane permeability for water at sub-zero temperatures. And you can actually use this to predict optimal cooling rates for cryopreservation of a specific cell type. We actually studied this for stellium sperm. For stellium sperm, you have what are referred to as good and poor, good and bad freezers. So that not refers to the whole animal, but just to the sperm of the animal. So there's a problem that some sperm from some stellium hardly survive freezing, whereas others you can easily cryopreserve. We tried to study this, if this is related to the sub-zero membrane phase behavior. So actually there's an empirical equation. So from these data, from this FTR data that I've shown before, you can derive membrane permeability parameters. I'm just very briefly explaining this, but from this you can derive these parameters and calculate optimal cooling rate you need for cryopreservation. We did this, the results were actually inconclusive. We could not really say, okay, pinpoint good and poor freezes based on membrane permeability at sub-zero temperatures. But anyway, it gives an interesting mechanistic tool to study physical properties of cells and at deep frozen temperatures. This I'm not probably gonna skip. Study we did on various cryoprotective agents, but I want to talk now a little bit, speed up a little bit now. But some recent studies we've done where we actually, so what we've shown that there's this drastic phase change, so membranes undergo phase change. If you, at the moment you have this ice nucleation. And what we thought, what we hypothesized, if you have such a drastic phase change, this creates a change in membrane permeability. So it cannot be that your membrane permeability here is the same as for a certain molecule as here. So we tested this hypothesis by looking at uptake of membrane impermeable compounds, such as trehalose again. We first used fluorescent dye, lucifer yellow, which is the same size as trehalose, to actually show proof of principle. And what you see is that if you stay at supra-zero temperatures, this dye is not being taken up. It actually is being taken up at 37, but that's why endocytosis. It's something different. If you freeze, you can see clearly there's an after thawing. You can see this fluorescence indicating that the dye has been taken up with very efficient, high efficiency. So molecules of about 500 Dalton are actually taken up during freezing. And we can actually take advantage of this. So it has always been believed trehalose is not taken up by membrane, but it is. If you freeze, cells take up trehalose in molecules of that size with high efficiency. We've actually studied this for, and here I show it for sperm. Stallion sperm takes up trehalose during freezing. It's always believed does not happen, but it does. After freezing and thawing, you can find a lot of trehalose inside the cells. And this is actually of interest. So we've studied this in fibroblasts, in stem cells, and in reproductive cells. I studied this with various collaborators. And this also allows cells to survive freezing with just trehalose as the sole cryoprotective agent. And this is very interesting because trehalose is non-toxic. So DMSO and most typical cryoprotective agents are toxic. So you need to remove them for various applications. Trehalose is non-toxic, it's a sugar. So, and it's actually also FDA approved. So you can, and that was our collaborator from the USA, company in the USA had an interest in this. You can cryopreserve a cell with trehalose alone. It's more complicated than with DMSO. You need to very carefully control the cooling rate. I've shown this over here. Again, you see this nice inverted U-shaped curve of cryosurvival. But it is a very narrow curve. With DMSO, it's much broader, it's much easier, but it can be done if you carefully control the cooling rate. We've actually, I'm not going to go into detail. We've shown the same principle in sperm, and it also you can use it to protect sperm during freezing. And we've actually, I'm going to speed up a little bit. We've actually used this to also look at freeze drying, and I'll show a few examples of this, how you can use this uptake of trehalose for dry preservation of cells, fibroblasts, sperm, and even some we also study whole. This to show what is freeze drying. It's a combination of freezing and drying. So I'm just going to briefly show how this works. We do actually, in this case, we do the freezing extern. So because every cell type has its own unique freezing rate, you cannot use the freeze dryer to do the freezing step. So we do this externally, and then what you do is you have pre-cooled shelves, and you put your sample on the pre-cooled shelves, and you keep the sample in the frozen state for a long time, and while you turn on the vacuum, and this allows sublimation. So that is how freeze drying works: sublimation of ice in a frozen product. And so you first remove the ice crystals, and then at a certain time you increase the shelf temperatures, going back to room temperature, and at the end you have removed all the water and dry products. This is how freeze-dried sperm looks. So this is how our pilot scale freeze dryer. These are shelves where you can put your sample and you can cool them to minus 60 degrees Celsius. But it's not practically to freeze dry. You do it around minus 30, because otherwise it takes too long. This is how it looks like. So after a day or so, it's a lengthy process. You can actually, So in about a day you can have your cells in freeze-dried state. This is a study we did on freeze-dried stallion sperm, protected with trehalose and not protected with trehalose. And well, first of all, if you freeze-dry sperm, it is not membrane intact anymore. They don't move anymore, so you can consider them as non-viable. However, DNA is still intact in freeze-dried sperm. There's a specific assay, SCSA, in this technique, but you can use this to look at DNA integrity in sperm. What you see is that directly after freeze drying, so this is just a normal buffer, where before you can, what is it, INRA, this is a standard buffer for sperm. If you freeze dry sperm, this is an indication, this flow cytometric assay, if you have your plot over here, and I have to look, it's difficult for me to see, I think this is green, there's green and red fluorescence. If it is fluorescent in this range, this means the DNA is intact. You can see that irrespective of the formulation, directly after freeze drying, also with sucrose, so this is the sucrose BSA formulation, DNA looks perfectly intact. So you would think, okay, I don't need my trehalose, but my DNA is intact anyway. However, if you look under accelerated aging conditions, that means at 37 degrees Celsius, you can see that after 1 month this curve starts to shift. And after 90 days, you can see that your DNA is completely gone. So you've lost all DNA integrity. And also in this other formulation where there's no protective agent, you can see this. With sucrose, in the sucrose BSA, you can see that your DNA remains intact even at 37 degrees. So this is very interesting. If you extrapolate, you can also think about it must be very stable if you store it at room temperature or at 4 degrees Celsius. Yeah, but okay, we don't have fully viable cells. That should be clear, but we can preserve our DNA. And we plan to use this also for ICSI, at least my collaborators at the vet school. This is another project that I'm just briefly touching on, that we do on preservation of saliva, dry preservation of saliva. What we want to do this for is, it's actually a very large study that's being done countrywide in Germany, is to study saliva from volunteers, actually, and then analyze the telomeres. So the telomeres is sort of the end of the DNA, and if you grow older, your telomeres will decrease in size. They will get shorter and shorter. And the idea is that if you do a lot of sport and you exercise, that they will grow a little bit longer again. So that's what we plan to analyze. So there's actually this combined with an exercise program. And what my part in this project is to have collect this DNA in a non-laboratory setting. So we want to send this out to sport people and to old people and various groups, and then ask them to send it back to samples. So we are looking into a method to dry samples, saliva, without having a freeze dryer. Not everyone has a freeze dryer at home, I think. So we actually have developed a filter drying method, where this is just simply the first preliminary experiments, but we have a new collection device based on a filter. And so if you don't have a freeze dryer, if you want to dry something, this helps, because if you put your sample on a filter, you increase the surface area and you decrease the vapor pressure of water, and this accelerates drying. You can see that within 3 minutes a certain droplet of a certain size is already dry, whereas if you have the same droplets and you don't have the filter, nothing happened. So this is something we're also working on for telomere analysis. Again, we don't have viable cells, but it really has some very interesting applications. We're also doing, in collaboration with Helmholtz Institute in Germany, I just recently started a project on lyobanking, so as an alternative for cold preservation, so liquid nitrogen store. We just started this, and could be big if there's an interest in this. And I've always mentioned this. A lot of biobanking you can actually replace by, if you know about the fundamentals, you can replace this by dry biobanking. And now there's a time that people are interested in this. If the biobank people are not interested, we're not going to move forward, but they're slowly getting interested in this. This is going to be my last example, a project on freeze-dried heart valve. That's a big project I've worked on. Heart valves are, there are 4 heart valves, and if one of your heart valves is not functional anymore, then they need to be replaced, because otherwise you will be in trouble, so it can cause serious diseases. So we have a method in Hanover, so Hanover Medical School has a method to decellularize heart valves, so take out the cells to reduce immune response. And now we have these heart valves in water, and so I was asked to find a way to preserve them, and we've actually found a way to freeze-dry heart valves from porcine, and we actually went already to animal studies with this. So this is a sheep that has an implanted freeze-dried heart valve that survived the procedure, and the freeze-dried heart valves function just as good as heart valves that have not been freeze-dried. Yes, of course these are acellular matrices, but it was already a challenge to freeze-dry these systems. I'm not going to go on to the details, but just to give you an example of the projects that we are working on. This brings me to the summarizing. So it's an exciting field, I think, drug preservation of mammalian cells and tissues. It is important, that's what I want to emphasize, to study fundamentals of this. Transport processes are very important. Permeability of water, cryoprotective agents and lyoprotective agents. Without fundamentals, we're not going to get there. And eventually, we'll probably need a combination. It's not a trivial thing, freeze-drying of mammalian cells to get fully functional cells. This will be a major thing if this happens. But it's an exciting area, and I think that this, with a lot of combining forces, this has great potential. Okay, thank you for your
Thank you very much, Professor Walker, for your really exciting talk. Are there any questions from the audience? Please. Professor Dainese.
I'm a biochemist, so really fascinating talk. Thank you for coming here. So actually, changing the membrane lipid composition, you can change also, during the cryopreservation, you can just change the cooling rate. You show exciting data concerning different cells and different cooling rate depending on the different kinds of cells. Actually, as a biochemist, we know, and you know already, that during the cryopreservation you lose some specific lipids during freezing thawing procedures. And so my question is divided in 2 parts. So the first one, have you never tried to check for the different cooling rate in different membrane composition cells, different cells with different membrane composition? And the second one, because we are working with, during freezing thawing procedure, we are changing also bioactive lipid composition. That means lipids that are able to change, let's say, lipid raft, some cellular compartmentalization, and also, the activation or inactivation of receptors that are located in the plasma membrane. And we never try to, go more into detail, from the biochemical point of view, in this kind of bioactive lipid composition, and also, in the change of this kind of membrane composition during cryopreservation.
Yes, we also studied actually also membrane modification strategies. Talking first of all, the membrane composition, I'm not sure if it changes during freezing thaw. What happens is you get accumulation of reactive oxygen species, and you get attack, free radical attack, and they're specifically acting on yes, but particularly I think one of the molecules that goes out easiest is cholesterol, and this affects cholesterol is probably the cholesterol rapidly moves from a cell to its extracellular environment. We've actually studied this using liposomes actually to modify, to supplement, looking at lipid transfer from liposomes to cells, and also cholesterol. Cholesterol goes easily, and you can use this to enrich cells with cholesterol or deplete them. And at some time it could provide a tool to increase stability of cell during cryopreservation. We've done studies with this on red blood cells, but also on sperm. That is has been well studied actually, membrane modification.
This is very interesting because cholesterol it has also dramatic effect on receptors.
Yes, because it affects the domain formation in cells. Yes, I've also looked at this some time again. There's some very interesting things that are related to this.
Thank you very much to both. Any more questions from the audience, from the students? Come on, please. Ask some questions. Actually, the aim of the project, inducing a reversible drying in cells, is very challenging. So I think it's an impossible mission for just a single group, a single specialty. That's why in DryStore we have Professor Walker is a biophysicist, so completely different. I'm a veterinarian with all my limits, and an embryologist. So we need a kind of really a synergy between biophysicists and engineers, or professional dryer like Imogen, and mostly models to look at. That will be really the only way to proceed. Drying cells by trial and error, it will take ages. I think we have either to join forces, otherwise it will be an impossible mission.
It is, and I only showed this one aspect of using a sugar trehalose.
Yeah.
But if you think about natural and hydrobiotic strategies, it's not only that, so it is much more complex, and it's really a challenge. So it's like landing on the moon. If you are able to achieve cryopreservation of, let's say, an embryo, it is.
It's challenging, isn't it? I have a couple of other questions for you, but I'll leave them for the afternoon. I have just a couple of curiosities, because naturally I was struck by you showed us the picture when the pigocytes were exposed to various cryoprotectants, okay? And then they shrunk in response to the water flux outside the cells. But if you treat them with what was it, trehalose? No, sucrose. Actually, the oocytes remain shrunk. It didn't naturally expand. Why? What is the reason why for it?
Because trehalose is non-permeating at super-zero temperature, so they only shrink. So because it does not get in. But the DMSO goes in, and then the cell starts to expand again. The trehalose, it only extracts water from the cells. That's why. So it does not.
Yeah,
it does not go back to its original position again.
No, that's a
maybe
complication.
if you wait very long, but then that is related to cell death.
Okay, that's very interesting. Also, actually, everybody is struggling now to get trehalose inside. You just show us. If you cool the membrane, actually goes. Can you actually manipulate it? I mean, can you regulate the trehalose upload by the cells? Or how much can you actually effectively pack into the cells?
With fibroblasts, we were able to get, if you have 300 outside, you get almost 150 millimole inside. So it's very high concentrations. Yeah, you could maybe even increase it a little more if you change the freezing protocol. You stay in the middle of the phase transition, for example, where you have the maximal membrane disturbance.
I see. For how long can you hold this opening of the membrane without damaging the cells, of course?
Not too long. It's very tricky. So if you're definitely able to get more in, but then the cell will die. Right. So that's the balance. Yeah.
Okay. Interesting. Thank you very much. More questions? Any more questions? Okay, I surrender. Thank you very much, Professor Walker. Thank you. Next speaker is Professor Alberto Cincotti from the University of Cagliari, and he's also an engineer, so he's going to tell us the point of view from the engineer approach for drying cells. Buon lavoro.
Okay, thank you, Professor Loy, for the introduction. I am a chemical engineer from University in Italy, and I have the difficult task in DryNet project to try to model the desiccation of the living cells to obtain viable cells. Of course, I will try my approach, which is the continuum approach, the engineering approach, and it is difficult for different reasons. I will try to explain why. And first, I will give you a brief outline of this talk. I started the DryNet project trying to perform a careful bibliographical search on the mathematical modeling of these techniques, and so I will show you my results, and so I will give you the state of the art on the modeling of desiccation, and I will finally explain what I'm trying to do for the DryNet project. Yes, this is the results of bibliographical search on the modeling of desiccation. The keywords are here indicated. I tried model with a star, because modeling with double L can be used in mathematical modeling, and the other ones are here indicated, model of the first one. And I came up with something like 120 papers in total. Most of them, 65% is on food. It's basically on food. I'm talking about modeling, okay? And so this was removed, simply because the product requirements for food engineering is, of course, not to be able to have viable cells at the end of a process. So I don't care. They don't care. Me neither. So I was focusing on the cells. The cells in general, and I came up with 41 papers, and then, but actually only 20 papers, or half of these 40 papers are on actually on mathematical modeling, because model it's a keyword which means also animal model, something like that. So it's just experimental. So I found, finally I have been reading very carefully 20 papers, and these are the systems investigated. I mean, it's just water, but most of all it's biopharmaceuticals modeling, so it's water, sugar and proteins. And unfortunately, there is no modeling on living cells. I mean, I'm talking about engineering modeling. All the phases considered, from lyoprotectant addiction, loading, then freezing, drying, primary or secondary, then radiation. I didn't find anything. That's it. So this is very disappointed. I have to start from nothing, trying to assemble the things. I have an experience on cryopreservation modeling. So I had to assemble the things, to study what phenomena takes place and what is important from the continuum engineering perspective. Unfortunately, there is another problem. I didn't find anything on drying. I mean, I'm talking about air drying, atmospheric drying, the one which I know is being used by the Japanese guy in the DryNet project. And The modeling I found is on freeze drying or spray freeze drying, which is a sort of freeze drying, just different the freezing phase. So this is basically the conclusion of this bibliographic research. There is no modeling focused on living cells, focused on optimizing the viability of the cells at the end of the process. And most of all, there is no modeling on drying, just drying, without freezing phase. Yes, this is the phase diagram of water, and just to explain what freeze drying means, you start from a liquid solution at ambient pressure, 1 atmosphere. You just decrease the temperature and you have freezing, of course. You move from the liquid phase to the solid phase, crossing this line. Then, after freezing, you have you reduce the pressure below the triple point, and you then increase the temperature for the primary and then again for the secondary drying. While for the drying process, you just move from here, the starting position, to here, reducing the relative humidity. So you go into the vapor phase in the phase diagram. The main difference between the two are, of course, the fact that two phase changes are on freeze drying, from liquid to solid, and then from solid to vapor. This is sublimation. This is freezing, and this is the sublimation. While during drying, you have from liquid to vapor, which is evaporation. So just one is different. And yeah, freeze drying is generally used instead of drying when you have heat-sensitive materials to work with, and so this is why they freeze the sample, and you use vacuum condition just to increase the water sublimation rate. That's it. Usually a lyoprotectant is used for cells is trialose, as Professor Volkers already told you, and it's sugar, and so you need an extra first phase, which is the trialose loading inside the cells, not only in the external solution. And to talk about the freezing phase, this is the phase diagram of the solution water and sugar. Here you have on the x-axis the percentage from 100% pure water to 100% pure sugar. So this is the composition changing from left to the right. And on the y-axis you have the temperature. This is the so-called temperature concentration phase diagram of binary solution at constant pressure, because it changes with the pressure, but this is at 1 atmosphere. And this curve, which starts from here, this is 0 point degrees, which is basically the melting temperature of pure water. And then if you increase the concentration, moving from left to right, the concentration of sugar, the melting temperature of the solution decreases. This is the freezing point depression, which is basically the mechanism for osmometer to work. And this is the liquidus line, this one here. Sorry, my hand is, I cannot point very well. This is the liquidus line. It is the solubility of sugar in liquid water, which increases with temperature. And this other one, starting from here, going up, is the glass transition temperature, which is a composition-dependent property. It increases with the increasing amount of sugar, so you have you can have a glass even at room temperature, which is here, somehow here. During the freezing phase, you start to have a freezing solution, a solid formation. So basically you decrease the temperature, and then the liquid solution here starts to increase in concentration with the sugar, because you have the sequestration of water which is going to do highs. This is the biphasic zone. And so you basically, during the freezing phase, you move from A to B, C, and D. Then, at relatively high cooling rates, you can overcome, go below the glass transition temperature, and you come up with the point E at the end of the freezing, which is sugar with some water. The first, sorry. Yeah, the first formation, the first solid formation is just pure ice, which is basically called free water in freeze drying, while the second one is water entrapped in the glassy matrix of the sugar, and it's called bound water. And during the drying phase, there are two phases: the primary drying and the secondary drying. First, the primary drying. You have the sublimation of free water. You go from pure water ice to water vapor. And then you have the secondary drying at the higher temperatures, which is the desorption of bound water, the water that was entrapped in the glass of the sugar, and goes to form water vapor. It happens at the higher temperatures. In the temperature composition phase diagram, you're basically moving from E to F. So increasing the temperature, but also increasing the amount of sugar in the glass. The secondary drying. The freeze dryer. The freeze dryer, the industrial one, it's a two-chamber machine. There is a drying chamber and another second chamber, which is the ice condenser. How does it work? First, the sample containing the solution, the aqueous solution, with the biomaterial to be preserved, is put in vials, which are put on these shelves, and then the temperature is decreased during the freezing phase by flowing a cold fluid inside the shelves. This way the free water crystallizes, while the bound water is entrapped in the glassy matrix. Then the chamber pressure here is decreased by decreasing this one. And also the temperature flowing through the shelves now is increased for the drying phase, and as a result you remove water vapor, which evaporates from here into the condenser, which is called the water vapor trap, and you get a dry sample, a so-called dried cake. This is a zooming in of what's going on from the engineering point of view. Basically, you have initially a frozen sample, which occupies all the volume of a sample. Then, with the drying phase, you heat it up, and evaporation starts, sublimation starts from the top surface, which is open. Then you have a moving interface. I mean, this interface goes downward, transforming the frozen sample into a dried cake, a porous dried cake. And so you're removing bound water from the porous dry cake, which is the glassy matrix, and instead the free water which is the primary drying of pure ice, is happening only in this infinitesimally thin interface between the dried cake and the frozen sample, while bound water is removed all over the dry cake. Yes, from the mathematical perspective, this is the Stefan problem, and I will skip all these things. I will talk only about the phenomena that are typically considered from an engineering point of view, and it's heat transport with conduction and convection through a porous medium, the porosity of the dry cake, but also radiation. Water transport, it's diffusion and convection through a porous cake. Convection, so transport in a porous media is a typical topic of chemical engineering, and also there is phase change, sublimation and desorption. During the drying, you transform the frozen sample in a dry cake. This means that heat and mass transport resistances increases in time, so you end up with a very high drying time of drying. It's a long phase that needs to be reduced as much as possible because it's expensive to maintain thermal and vacuum, and what is normally done is just to keep during the drying phase the pressure here in the condenser as low as possible, to trap as much as possible water vapor in this condenser, and the temperature during drying is increased as much as possible, but not too much, because otherwise you're going to have the collapse of a porous glassy matrix, because you overcome the glass transition temperature once again. So typically these operating conditions, the optimum of this operating condition from the engineering point of view was obtained by a trial and error strategy, but nowadays more increasingly is mathematical modeling adopted. Mathematical modeling will usually addresses only the drying phase. I don't know, freezing and radiation phases are not considered, and volumic variations of a sample are typically neglected. And this is the model that was developed in 1979, so quite times ago. It was the sorption sublimation model by Liapis and Lichfield. I will skip the equation because I don't think the audience is actually responsive to this matter, but I mean, these are the equations of the phenomena I was talking about that are typically taken into account for the freeze drying, and yeah, these are the typical results that can be obtained. The spatial temporal profile of temperature inside the sample, or for example the concentration of bound water, which is which is happening only in the dried cake, which is increasing in volume. So that's why it's only here during the drying time. And these results are really important from the industrial point of view, because you don't know exactly what is the temperature inside the sample, and when you have to change, for example, increasing the temperature from primary drying to secondary drying. So this is really important results. These are the results, a comparison between experimental measurements and theoretical results. The model is able to follow very tightly the measurements. This is amount of water removed in time, and these are other results like desorption rate, residual moisture, or product temperature. In every case, you see the model is able to follow the system behavior. I will briefly talk about spray freeze dryer. spray freeze dryer is like freeze drying, just the difference is the freezing phase. You basically forms with an atomizing nozzle aerosol by spraying the droplets of liquid in a freezing medium like nitrogen or cold gas stream, and you basically come up with a slurry of frozen particles. So they are collected, packed in containers, and transferred to a freeze dryer for the drying phase. And the main difference is that the frozen sample is not a block of ice, it's just a porous packed bed of frozen particles, something like this. This is the difference. So from a mathematical modeling point of view, the difference is that in the frozen part of a sample, you have a porous, like a dried cake. So you have to take into account heat and mass transport even in the frozen layer of a sample during the drying process. I will skip the equations because I don't think it's a good idea. And yeah, the conclusion: there is no modeling on living cells. There is no modeling on preservation of viability. There is no modeling on air drying. There is just modeling on the freeze drying, and specifically there is modeling only for the drying phases, not the freezing or the rehydration. So in the framework of the DryNet project, we have been developing a model to take into account the cell's viability by borrowing from literature of cryopreservation and the experimental papers on drying of living cells or freeze drying, like the papers of Professor Volkers. So we basically want to consider the osmotic behavior of the cells, to take into account two possible injuries to the cells: the solution injury or the crystallization injury. Solution injury is the excessive excursion on cell volume during osmotic shrinkage or swelling, so during dehydration or rehydration, and also excessive excursion on solutes concentrations. And the crystallization injury is the formation of a crystal of sugar instead of glass, which is supposed to be a killer for the cells. So we think that at the end of this project we will be able to predict final cells viability. The system we are focusing on is the dryer, which is used by the Japanese guy, Professor Kikawada. This is the dryer. It's a desiccator unit, a commercial one, which is used inside an incubator at constant pressure and temperature. Basically, after trialose loading to cells, and Professor Kikawada uses osmotic loading at room temperature. It lasts 2 days at 37 degrees. And after this trialose loading, the cell suspension is put inside this desiccator unit with an adsorbent, which is silica gel here at the bottom, and then everything is put inside an incubator for something like 7 days. And the adsorbent here, the silica gel, is used as a water vapor trap, and so it reduces the relative humidity in the chamber and desiccates the cells. But what is more important is that Professor Kikawada wants to have a slow evaporation. So the petri dish containing the cells solution, it's covered but with a lid, but not sealed around the edges. So the moisture may be adsorbed by the adsorbent here down at the bottom of the dryer. This is what we think is going on the system. This is not in scale, of course. This is the adsorbent, and this is the petri dish containing the solution of the cells, and this is the chamber of the desiccator unit. Water vapor is removed from the chamber by the adsorbent, lowering the relative humidity in the chamber. The difference between the relative humidity in the chamber and the relative humidity in the gaseous part of the petri dish is the driving force for the leak of water vapor, and the difference between 100% saturation of the liquid and the relative humidity of this gas phase is the driving force for the evaporation. And as water evaporates, the solution level decreases, while solute concentration in the liquid increases, and so this triggers the osmotic shrinkage of the cells, which becomes shrunk, and later, as evaporation continues, solutes in the extracellular compartment overcomes the solubility limit of the system at the system temperature, so a solid formation starts. At the end of the day, you come up with dried cells, shrunk, and solids that are present at the bottom of the petri. For the radiation phase, you just invert the sequence of what's going on, what I explained now, and that's it. So you don't have osmotic shrinkage, but you have osmotic swelling. Simplifying assumption, the current status of this model is that we are considering perfect mixing, temperature and pressure is constant. The chamber, the desiccator unit doesn't have any leak, so the material is, there is no material exchange with the incubator, and we are not considering the absorption of bound water right now, and we are not considering right now, but we have to do that. The solid formation in intracellular compartment, but only in the outside, in the extracellular compartment. And we are using for osmosis the classic 2 parameters model. These are the equations. I just want to skip as before because I don't think it's a good idea. And we come up with this. Yeah, there is in general a possibility to have basically 2 extreme conditions. The first one is when you have an evaporation rate very slow in comparison with the crystallization rate. So the liquid solution starts from here, then it overcomes the solubility limit of sugar in the water, and basically this is a very long process, and you come up with very shrunk cells and sugar crystals outside and inside the cells. This situation is a killer for the cells, and it's typically called a solution injury for the cells. At the other extreme, you have an evaporation rate which is very fast. Now the cell move, increasing the sugar concentration from here to here, and you come up with unshrunk cells and glass formation. So you don't leave the osmosis to have the time, you don't leave the time to equilibrate with the increasing solute concentration of the extracellular compartment. And in the middle, with an evaporation rate which is not very slow, not very high, you can have different results. Basically, you have slightly shrunk cells during drying, and you can come up with sugar crystals or glass depending on the different things. These things are are many, including volume of phases and geometries, but most of all, the most important one is the evaporation rate, which we think may be changed to find an optimum in medium values from a minimum viability of a solution entity, which is taking place at a very slow evaporation rate, and a maximum evaporation rate where we have a crystallization injury. So you have to tune evaporation rate at this optimum. This optimum depends, however, on many things: relative volumes, the amount of adsorbent you're using, the concentrations of solutes and cells, the initial ones, but it varies from a cell injury to another because membrane water permeability varies, and our final idea is to take into account also the distribution of cells. The cells are not of the same volume, and we think that smaller cells will suffer more of solution injury. Larger cells, the mothers in the mitotic cycle, will suffer more of crystallization injury. And when you have to optimize the system, you're going to have to optimize this area under this curve, this volumetric distribution, which are going to be the viable cells. Yeah, this is my research group in the DryNet project, and I thank you for the attention.
Thank you, Alberto, for the presentation. I thank you for skipping quickly all the formulas. Yes, no, I'm kidding. You know, I would like really to know, but my brain really is quite resistant to mathematics. Any questions from the audience? Luca.
Very nice talk. Just one curiosity from an engineering point of view. How much is important the surface area for the sublimation during the sublimation stage? What is your opinion?
It's extremely important because if you increase the area, you're going to increase the water removal rate. So it's very important. In fact, many people they use small samples, which basically means that the ratio between area and volume is increased, and just to favor the evaporation rate. It's extremely important. Everything depends on the sizes, the geometries also, and yeah, I think that a trial and error strategy is not gonna it's not gonna succeed. You have to calibrate everything, and it's a difficult task. Also from the engineering point of view, to find the optimum.
More? Wim?
Yeah, I just have maybe more of a comment. But probably freeze drying of a living cell has not a lot has been done in modeling from a modeling perspective. But what has been done is in the freezing part has been studied actually already by Peter Mason quite extensively.
Yeah.
He has shown that actually cell volume response during freezing, so at sub-zero temperatures. He's shown that you have cell survival if you have cell shrinkage of 95% at minus 30 degrees Celsius, right? So he actually does a model for this.
Yeah.
So that could be a good starting point.
Yeah, sure.
You know, this water transport model, so that's the Arrhenius equation of the LP.
Right.
And this, so that could be a good starting point. You know, at that point, for optimal survival, that's your state of the cell, and then you apply the vacuum.
Yeah, I need to assemble the things because no one before did already or tried already to perform everything from the engineering point of view, considering all the phases. So I need to put them up and try to think to see if it works. Yeah.
More questions? So I understand you tend to favor air drying comparing to freeze drying.
Well, as far as I know, Giorgio Ligios, Dr. Ligios went to the Japanese partner, and this is what they are doing. They are not doing freeze drying, they are just doing air drying at ambient pressure and temperature. And so I thought that initially that's the starting point. I tried to do drying, also because there is nothing on the literature about this. So
that's why you're here.
Yeah. So yeah, it's challenging, of course. I don't know if I can succeed, but I will try. I mean, I need many things from the molecular dynamic simulations. He knows that. Yeah, because if I don't have any measurement, I need at least a prediction. And,
yeah. But one of the variable important for you, which I don't think is such as a biologist, because you say cell volume. Don't expect to find a huge cells and small cells. I think there are the variation of the cell volume during the cell cycle. They are there, but not really so. I don't know. They don't get twice as much bigger.
In terms of mass, the daughters are just the half of the mothers. So
yeah, but you can actually work it out.
Of diameter, maybe you're right, because
that's not an issue.
With the third power of the diameter, but it's different. I mean, you have it's not like this, of course. This is a Gauss, the Bell distribution. It's not like this. It's a log normal distribution, which has its maximum at the smaller volumes, because you have more daughters than mothers of the mitotic cycle. So I expect something like this. I mean, if you take into account the cell volume distribution, smaller cells are going to be killed by solution injury.
Yeah, but
because the ratio in those cells between the area and the volume is increased in comparison with the bigger ones, and the solution injury is a surface problem.
But if I'll tell you, look, I give you a cell population which are very uniform, because a cell biologist can synchronize the cells. I can give you G1 small cells, I can give you G2 cells, I can manage to really to give you just a single size. Will that make any better?
You put them in G0.
Yes, also.
Yeah, but just not to do that.
It will make it better.
Well, you're going to have just one size, then you're not going to have a difference between the smaller and larger, so you have to calibrate more precisely the optimum in the evaporation rate, just to have that size surviving. You know?
Okay.
That's it.
Thank you. More questions? So I understand now there is a coffee break, right? And then we will, please be all back, because the interesting part is still to come, so it's a very interesting workshop. So all the students and everybody, please be back in 15 minutes. Do you have something to?
For the students.
What? Oh, questionnaire, oh yeah. All the students are kindly requested to fill in a questionnaire, because for conferring you the credits, we will need to exhibit to the presidency. So please take all the modules, all the forms, and fill in. They are very simple questions. Everybody can answer them. And do it over coffee time and be back 15 minutes? 15 minutes, okay? Thank you very much, and see you later. Somebody's missing from DryNet stuff. Let's wait a little bit. 2 minutes, then we will start. Ragazzi, state capendo qualcosa, sì? Quindi seguite le diapositive, magari questo vi aiuta un po' a seguire il discorso e poi intervenite, insomma, siate partecipi, per favore. Is there? Okay, I think almost everybody is back. Welcome back, everybody. And so, next speaker is Professor Santiago Aparicio. I think he's not on the program because yesterday night we discussed about the DryNet, the project, the philosophy, and then actually I'm very curious. I guess you all are. Our biophysicists can actually, what can tell us to do, you know, to help, or maybe better, to help us to reach our goal to induce a reversible drying. So let me thank you very much, Santiago, for your kindness, this very last minute talk, and please, floor is yours.
Okay, thank you, Professor. First of all, thank you for your invitation, for giving this talk. As you have explained, this is a last-minute talk, so I have assembled a few slides describing some of our ongoing research in the field of molecular modeling of nanosystems related with drying procedures into the DryNet project. So I come from the University of Burgos and the Institute of Critical Advanced Materials at the same university, and we are a group specialized in molecular modeling, theoretical modeling of many different kinds of phenomena in relationship with materials of science, energy, environment, and in the DryNet project we are in charge of the molecular modeling studies of this kind of phenomena that has been described by Professor Borges and Cinquotti in the mesoscale. So I have entitled this talk Nanoscopic Vision on the Lipid Bilayer Structure Interacted with Trialose Water Mixtures. What I mean with nanoscopic vision is vision at the nanometer scale. So the description of the drying problems that had been given by Professor Borges and Professor Cinquotti is in the engineering or macroscopic scale. So we are theoretical chemists and theoretical physicists, and we go to the bottom of the scale. We work with atoms and we work with molecules. So we try to obtain information about what's happening at that scale. So how molecules interact with different systems in order to obtain the information about how these systems are arranged. So I have described it in this initial slide, our scope, our objectives. What do we want to do with the simulation? Our studies are theoretical efforts. So we are theoretical scientists. We work with supercomputers. We go with mathematical models. So we do all our studies in silico. What we call in silico means that studies using computing techniques. So we use supercomputers for modeling this kind of systems, and the objective is analyze the mechanism of action of seroprotectants. So we want to obtain a molecular level picture of the behavior of these systems in order mainly to analyze the structure, provide information that can fit the models developed, for example, by Professor Cinquotti, and to obtain a detailed vision of what's happening at the molecular level. Our final objective is this one is very important for us. We are talking in this presentation about one of the most important seroprotectants that has been used in the academia and in the industry for drying purposes, that's trialose. But we want to go further. We want to design new kind of seroprotectant who mimic seroprotectants in nature. So for this purpose, it's very important the development of tools, mathematical tools, modeling tools that allow us to infer the properties of new seroprotectant using pure in silico approach. That means using only computers. computers that provide information about the physicochemical parameters, about the structure of the fluids, about the interaction with biological structure, with relevant biological structure like membranes, in order to check the behavior of different seroprotectants, in order to infer the most suitable condition, the most suitable molecule, and all these properties. So in this presentation, we are going to show some initial results of our studies within the DryNet project, in which we analyze the interaction of the most important seroprotectant, trialose, in relationship with this behavior with membranes, with molecular membranes, with cell membranes, because, as has been explained in the previous talks, membranes are the pivotal parameter, the behavior of membranes are the pivotal parameter, because they are the primary target of cell injury. So when cells are dried, this is the most important parameter that should be controlled. So we start from an initial hypothesis that has been previously mentioned, that seroprotectant, like trialose, can protect cells from damage. So this is the role of the seroprotectant, the behavior of the interaction of this seroprotectant with membranes in order to protect the membranes, in order to allow to efficient dehydration process. No? Mainly the two main processes that have been proposed for analyzing, for describing the behavior of drying mechanisms try to infer the molecular level behavior of these systems. But we consider that the most relevant model for describing this kind of drying processes is the water replacement mechanism. So we are going to analyze the behavior of membranes in order to see the molecular level effects of these water replacement parameters and water replacement modeling of the interaction of seroprotectants with model membranes. So basically, our objectives are these three main ones in order to characterize this kind of system. The first one is obviously to obtain a molecular level picture of the mechanism of interaction. We have the membranes, we have the seroprotectant solutions in water. Basically, what we want to do is, we want to know is what's happening at the molecular level, how the molecules interact with the membrane, how the molecules penetrate through the membrane, which is the molecular level behavior. So we are theoretical chemists, we are theoretical physicists, so we obtain a picture at this atomic and molecular level. We work with atoms, we work with molecules. If we have an idea of what we are modeling, we may have in mind that it's not possible to model a whole cell. So it's a cell, I don't care the type of cell, is a huge structure for molecular modeling study. It contains millions of atoms. So it's not possible to obtain a picture using mathematical modeling or theoretical modeling studies of this kind of system. They are too big for us. It may take years to model them. So what we do is we design some kind of models who mimic the structures that we want to model, in this case membranes, in order to obtain realistic results in reasonable time frames. So we want to obtain results in time frames of weeks or more, not in years. So it's not possible to model large, the whole cell. If not, we model a small structure, membranes, proteins, with a small size, to be able to obtain computational results in a short framework. So with this kind of model, we obtain a molecular level picture. So we see and we analyze how each model interacts with each other molecule, which is not possible to be obtained from pure experimental study. It's very difficult to obtain a picture of what's happening at the membrane structure, at the interface of the protein, if we don't use molecular modeling studies, because we cannot obtain this information, or we cannot obtain it in a direct way. So with this kind of studies, we are able to obtain a molecular picture. What's happening? How each molecule interacts with the other molecule, if they are bonded, if they change the orientation, if they change the hydrogen bonding, which is pivotal for this kind of system. And we can analyze different seroprotectants in water solution at different concentrations as a function of pressure and temperature. So this is our objective. How the structure changes with all the parameters that control the drying process. I mean, concentration, pressure, temperature, and the structure of the bilayer, and the structure of the membrane if we are studying membrane models, for example. No? So with this information, the information about the interaction mechanisms between the seroprotectants, water, and the membrane and the proteins, we are able to understand how the membrane structure changes with the interaction with the seroprotectant. In this case of this initial study, with triallose molecule as a function of composition, as a function of pressure, as a function of temperature. So we want to analyze these mechanisms, and we are able to see what's happening. Is the water replacement mechanism the true behavior of this kind of system, or there is something more relevant that's happening at the molecular level that we are not seeing using experimental technique, which give us, let's say, mesoscopic or macroscopic information about the structure of this kind of materials. So these are our objectives. So obtaining a molecular level picture and giving information about how molecules interact between them. I know that the audience is more oriented to veterinary and medical science, so I'm not going to put a single equation on this presentation, but all our work is mainly mathematical. So we are using mathematical models for describing the behavior of molecules and for describing the structure of this kind of system. For starting, I would like to give you some information about how we model without using any mathematical equation. Our theoretical efforts use two main different approaches. The first one is what we call density functional theory. For example, we have one of our models. In this case, we are modeling, this is a membrane structure. As I have said before, we cannot model the whole structure, we cannot model the whole cell. So what we use is we define a model that is big for obtain or for contain all the information of this kind of systems, but not too big. In this case, we are modeling a membrane. You can see here the membrane structure. You can see in this case is DMPC, there's myristoyl phospholipid bilayers, in which we have a lipid bilayer, typical lipid bilayer, in which we have the lipid groups here, the lipid molecules. We have the head groups, the phosphate group, the choline groups on top of it, and this is the outside, and this is the inside of the cell. And outside and inside, we put the solutions that we want to model. We put the solution, for example, in this case, in this kind of system, we have a water triallose solution at different concentrations of the seroprotectant. In this case, of triallose. In another kind of experiment, we can put here another different kind of molecules. We can put latent regenerative peptides, as we will mention later, or any other kind of solute. So what we define is using a method that we call molecular dynamic simulation, the dynamic behavior of this kind of systems. So we study how molecules move as a function of time, as a function of pressure, as a function of temperature. This is an atomic level modeling. As you can see, we have the water molecules, we have the solute in the liquid phase, we have the acyl tails of the lipid bilayer, we have the head group. We describe this structure atom per atom. So this is a true behavior of this kind of systems. It's not any simplified model. We define the behavior of the membrane as the behavior of each atom in each molecule. So we can have systems containing, for example, in a typical simulation, 1 million, 2 million of atoms. So this is too big. It's not as big as a cell, but this is realistic for describing the behavior of lipid bilayers. In this case, we have, for example, in the case of the modeling the interaction between a liquid solution, a theoretical seroprotectant solution at different concentration interacting with the membrane, we study how this liquid layer interact with the membrane, how molecules penetrate through the membrane from outside to inside the cell. Imagine this is the wall of the cell, the membrane of the cell. We put the solution outside and inside, and we are able to see how molecules diffuse through the membrane, how molecules interact in the interface, how these water molecules and the seroprotectant molecule, in this case triallose, are interacting with the lipid bilayer, how these molecules are hydrogen bonded in the surface, how they penetrate, and most important, how do they change the structure of the bilayer. So what we want to see is what happens when we put this membrane model in contact with a water solution containing seroprotectants. Is the structure of the bilayer changed? The phenomena that has been explained in the first talk by Professor Walker, how the acyl change of the lipid molecules interact between them. Do they collapse and they tend to a helification process or not? Or do they protect? These molecules are able to protect by interacting with the bilayer, by interacting with the lipid bilayer, this collapse, this interaction changing from liquid-like to gel-like. So this is what we want to obtain. How are we able to describe this interaction is the key for this process. So these are our models in which we change the structure of the bilayer. For example, this is example for one type of lipid, the MPC. We make studies with different type of lipids, POPC, whatever, and we are able to create mixed bilayers. As it had been mentioned before, we can put cholesterol molecules in the lipid bilayer at different concentrations, and to see how the structure of the bilayer changes as a function of the structure of the lipid bilayer content. We can change the type of molecules present here, trialose and other kind of seroprotectant, different concentration, and we analyze its behavior purely in silico. You must have in mind that all of this is made in a computer, in a supercomputer, but in a computer. There is no experimental studies. We describe each atom, each molecule, atom per atom. So we are able to take this picture of this kind of system. This kind of simulation are typical for these two molecules, which are very important for describing lipid membranes. This is the MPC. You see the acyl chains, which are this one oriented in this direction. You can see the head groups of the lipid, which are oriented to this direction, here and here. And this is the structure of the seroprotectant that had been previously mentioned, trialose, sugar, which is the most common seroprotectant, the most important seroprotectant, which is placed here in this region for different concentration. So this is our starting models. So for doing this, we prepare a collection of simulations with different physical conditions. For example, I'm showing you the initial simulation that we have been running this last week in our supercomputers, in which we are modeling different degrees of hydration. For example, we have studied full hydrated bilayers, in which we have a number of lipid molecules interacted with water, pure water, for example, as a reference, in absence of the seroprotectant, in absence of the trialose molecules. For example, in this case, at a ratio, water to lipid, around 27-28, which is close to the real behavior of liquid cell membranes. We have been modeling intermediate degrees of hydration, in which we decrease the number of water molecules, and we change the number of seroprotectant molecules in order to see the effect of the seroprotectant on the structure at lipid to water to lipid ratio around 12, and we study low concentration mixtures, in which we decrease even further the number of water molecules, and we change the number of molecules. So we have 3 different degrees of hydration: high hydration, intermediate hydration, and low hydration, 4 different degrees of trialose concentration. So in this way, we are able to see, we are able to mimic at the molecular level something close to the industrial level drying process, or cross in the initial stage. So at a fixed pressure, for example, and at fixed temperature. So if we want to do, we can model this system close to biological temperature, and going below, going to the temperature that had been previously mentioned for drying purposes, and we can see how the structure changes. So these are our model. No? How we do this? First of all, our main method is what we call classical molecular dynamics simulation. I don't want to give you any equation, any mathematical model, but this is a classic mechanic method. So we describe each atom and the interaction between each atom using a Newtonian mechanic method, basically. So in this case, for applying this kind of simulations, we need to know a collection of parameters for every single atom present in this structure. So we need to know the parameters, charge, the bonding parameters, all the molecular level parameters for all the atoms, all the molecules involved in the simulation. So this is pretty complex, because we need to have this information for all the atoms involved in this kind of simulation. We need to obtain a good model for giving a realistic picture of this kind of system. So all the results coming from molecular dynamics comes from the quality of the parameters that we use for describing the properties of every atom involved in the interactions. So if we use bad model parameters, results are not physically realistic. So we need to, the first step in our simulation is to use parameters which can be inferred from, as I said, I will explain later, from another kind of calculation, but which are realistic pictures of the real behavior of these atoms. Because if not, we are not describing how each molecule interacts between them. So we do this through mathematical modeling, as I will explain later, but this is the key. We carry out simulation in different what we call ensemble. Ensemble, from the viewpoint of statistical mechanics, are the methods that we use to control pressure and temperature. For example, we can start at close to biological temperature and ambient pressure, and we can go low temperature, and we can decrease pressure just for simulating at the molecular level the industrial drying processes. So this is our method that can be used to mimic industrial level drying processes, but obtaining molecular level information. We must have in mind that these systems are very, very large. Although we have said that we cannot model whole cells, we are modeling just small pieces of the membranes in this case. For example, imagine that this is a small piece, but this is very large. So it contains between 100,000 atoms to 1, 2, 3 million of atoms. So this is too large. This is a very computationally demanding problem from the viewpoint of theoretical chemistry. So we need to use a very efficient computational method. Now this is a problem. This is a problem for the modeling of any biological process problem, but this is a particularly important problem for this kind of system. We have to model very large systems, a lot of atoms, for very long times. For defining the processes, for analyzing the processes which happen in this kind of systems, we need to model to what we call microsecond range. So if not, we can see the real behavior of the system. So this is computationally demanding. It requires very big computers, large supercomputers, and in fact, we are designing or we are moving our simulations from traditional CPU simulations to simulations using graphic process unit, which are faster, which allow us to model these kind of systems. So if you check the literature on this kind of modeling, the literature is very, very limited. There are a few studies on this kind of system, and the studies are limited to reduce number of systems for a small number of atoms for not too large simulation times, which does not provide all the required information. So what we are trying to do is to model large systems for a long time to mimic the real behavior of this system. And this is not a simple task in terms of computational resources. So we need large supercomputers and a lot of time for doing this. So you may have in mind that although we are talking in silico, it's not as simple as putting results and waiting for putting a calculation and waiting for a result in an hour. It may take weeks for obtaining this kind of results. So we have to design all the simulation that we want to do in order to decrease the simulation time. As I have explained you before, the key for all these kind of simulations is what we call the for file. The for file is the mathematical model. I don't give you any equation, but it's just something like a mathematical model describing the properties of every single atom involved in the simulation. So we need to have all these parameters for all the atoms. And it's not a simple task, because if we use what we call unrealistic for files, results are far from the experimental result, because we are not describing the physics of the process. So we need to use close to real behavior of the atoms. No? So this is the key for obtaining realistic simulation, for obtaining realistic results. In the case of modeling the interaction between seroprotectant and model membranes, we have three different kinds of for files. Those describing the lipid molecules, these ones, do you remember? Something like this. We need to describe all the structure, all the parameters for all the atoms. You may imagine that this is a big molecule, so we have a huge collection of parameters for describing all the atoms, all the charges, all the bond, all the internal parameters of the molecule. That can be even thousands parameters for each molecule. Even for a small molecule like trialose, we have a lot of parameters that we have to calculate previously before going to molecular dynamic simulation. For doing this, what we have done in this initial stage is to prepare realistic for files. If you check the literature previously to this year, the reduced number of molecular dynamic simulation use a version of the for file, what we call CHARM 27 or CHARM 30C, which is the, let's say, the most used for file for this kind of molecule. But this model is not very realistic describing the properties of this kind of system. So what we have done is to define a new parameterization for the lipids involved in this kind of membranes. For that, what we do is, previously to molecular dynamics simulation, we use quantum chemistry methods to calculate all the parameters. So we need to model all the molecules, in this case lipid molecules like this. We do quantum chemistry calculations for this kind of molecule For all the atoms, what we do is we minimize the structure according to quantum chemistry methods. We obtain the charge, we obtain the structure, no, the bond distances, all the parameters, and with these parameters we fit the molecular dynamic simulation. This model, the model that we have developed, is more realistic in order to reproduce the important parameters for the membrane structure, like lipid bilayer area per lipid, for example, which is key to analyze the structure of the lipid bilayer of the membrane. So we have developed, we have modified this file in order to obtain a better description of the membrane structure. The previous parameterization wasn't too good. It wasn't bad, but it wasn't too good. So if we want to describe how acyl chains interact between them, which is the pivotal parameter for describing what happened when we put trialose water concentration. So as Professor Workes had explained, we have something liquid-like, or they collapse, and we have some hell, and everything is done, so everything is finished. So we need to see how these molecules interact. So for describing how these molecules interact, we need to obtain accurate parameters of interaction between these acyl chains. And this is an important and pivotal step in our simulation. We need to describe physically realistic models. And for this purpose, we have used this kind of calculation, which are also very computationally demanding. So it takes a lot of time to obtain all the parameters for such a big molecule like that lipid, or for the other lipids that we are studying in our current studies. There is another problem. The second type of molecule that we are using in our simulation is water, of course. No? And we may think that water is just oxygen bonded to a hydrogen molecule, so this is a pretty simple molecule, so we can model it very easily. This is not a good idea. Water is a simple molecule from the viewpoint of its structure, just oxygen bonded to hydrogen, but from the description of its properties using molecular dynamics is extremely complex. So if you check the literature, you may find up to 40, 50 different models to model water molecules, which it may be a little disrupting. So it's a simple molecule, and we don't know how it behaves. That's true. So water is in the liquid state, mainly in the liquid state, is a pretty complex fluid. So we need to use a water model which is able to describe the behavior of biological medium. So, and this is very important because different water models give different results. It may have no sense, but that's how it is. So we are using a modification also of one of the traditional models of water, what we call flexible HPC water, which is giving very good results when mixed with this kind of model for the force file of the liquid molecules, which is able to reproduce the X structure of lipid bilayers. So we are comparing, we have made previous simulation comparing the main parameters of a membrane from our models with this kind of modeling in comparison with experimental results, properties like area per lipid, like surface properties, etc. And they are very, very close. So we conclude that this is a good model. And finally, we have to design another force file, another model for the zero protector. In this case, for trialose, we have developed a new force file in the line of charm force file in order to obtain an homogeneous picture of the whole system. In this way, we are able to describe a physically realistic model for this kind of system. And of course, what we do is a previous validation study using comparing our properties, the predicted properties, the properties obtained from molecular dynamic simulation compared with theoretical, with experimental results. In this case, results are close to experiments, so we conclude that our model is a good description of the behavior of this kind of system. So, realistic model, long simulation, big systems. These are the three steps, the three key steps for obtaining a good description of this kind of complex model, and that's what we are doing currently within the DryNet, the DryNet project. So, sorry, we are at the initial stage of this project. We have started the simulation just at the beginning of the year, although we have some previous results. But I just want to give you some initial results to show you what we are doing now. For example, when we model this kind of systems, a very important parameter for describing the phase changes as a function of the presence of the trialose water solution is the changes in the area per lipid parameter. The area per lipid gives information about if chain molecules are separated in a liquid-like state or they are close in a gel-like state. So for this purpose, for example, I'll show you the results of these initial simulations in which we have calculated the area per lipid as a function of the iteration range and as a function of the triallose content. For example, you have the red square results in which we saw the area per lipid for fully iterated membrane, so membrane previously to the drying process, in which we obtain a parameter close to 0.7, which is a good parameter, close to experimental result. And we can see as we decrease the degree of iteration in absence of a triallose molecule, we see a decrease of the area per lipid. It means that molecules are something like this and they tend to approach. That's what it means. But this parameter for the lowest degree of iteration, which is close to the lowest degree of iteration that we are going to obtain for experiment, is above the helification parameter. So it means that even for this concentration, we do not observe helification. So we are obtaining results in absence of triallose that does not show helification of this kind of materials, because although in decreasing the iteration, decrease the area per lipid, but above the minimum value considering as a reference for helification purposes. In the case of the presence of triallose, you have different triallose content. We have triallose content, what we call T1, T2, T3, different triallose content at different concentration. We see that the effect of triallose in most of the cases is the increase of the area per lipid. So they disrupt the structure of the bilayer. It's changing the structure of the bilayer. And it's changing in a very complex way, because for low concentration, it increases. You compare, for example, the value 0.75 with the value of 0.68 in absence and in presence of the triallose at low concentration. You can see how area per lipid increasing. And then when you increase the number of triallose molecule, when you increase the concentration of the seroprotectant molecule, you see how it decreases. For this and for this purpose. But in all the cases, they are above the helification limit. So we obtain two main conclusions that we are not going to discuss it now because we are at this initial stage, but mainly the role of the triallose molecule is replacing water molecule, changing the properties of the bilayer structure, but maintaining the lipid molecules above the helification limit. So preserving the structure, although disrupting the structure, minimal disruption of the structure, but preserving the structure below and beyond the helification limit. So this is very important, because we are able to see, now doing further analysis, how is the structure of the bilayer that justify this kind of behavior. How are seroprotectant molecules interacting with the bilayer? How are these molecules bonding to this surface, to this interface between the membrane? What's happening with the water molecules here? What's happening with the triallose molecules there? And how the physical parameters like area per lipid, like diffusion, like the orientation of the lipid vectors change as a function of the presence of the triallose molecule at different concentration, at different pressures, at different temperature. So we are able to define, to obtain, to infer the most suitable condition for doing this kind of drying from the molecular viewpoint. So how they interact, going to mesoscopic and to macroscopic scale is the key for this kind of simulation. We can also obtain physicochemical parameters. We are able to see how these molecules penetrate through this membrane. So we are able to calculate the permeabilities of these kind of molecules, which can fit a general level calculation, as Professor Cinquote has mentioned. So we can provide data that can be used for modeling in general level processes. So this is the main result that we can obtain with this kind of system. For example, we can in this picture you can see the density profiles across the membrane. If you see the initial structure, we can calculate the density profiles across this membrane as a function of the concentration and as a function of the simulation conditions. This is a typical result at the initial stage of the simulations, in which you can see this is the central area showing the acyl chains of the lipid molecules. You can see the water concentration close to the surface, and you can see the peaks showing the absorption of triallose molecules at the interface on top of the membrane at the initial stage of the simulation. And after that we can see how this evolves, how these peaks evolve with the molecules diffusing through the membrane at different diffusion rates. So we are able to infer this kind of parameters. So the behavior of these parameters these molecules start from the densification of triallose molecules, which is clear from this kind of peaks that you can see here. It means that molecules are concentrated at the interface, thus disrupting the interface, which will explain these changes in the area per lipid parameters. And after that, we can see how these peaks evolve as a function of time, as a function of concentration, as a function of pressure, as a function of temperature. So that's our theoretical approach. So once we have defined the force file for this kind of systems, which is a time-consuming effort, we are able to model all the behavior for all these systems in order to obtain structural parameters and physicochemical parameters. These are our two main objectives. I don't want to give you more details because we are in the initial stage of this simulations study for this kind of project. But our ongoing studies, our studies that we are currently running in our supercomputers are trying to consider these three main effects. These three effects that are listed in this slide. No? First of all, we are going from simple membrane models, from these models using one type of liquid, for example, to mixtures of for example, mixture containing different types of different concentrations of cholesterol, different types of liquid, in order to obtain realistic membrane models. So we want to design a realistic membrane to mimic the behavior of a real membrane. We are also considering different carbohydrate contents, or the presence of different elements in the membrane, like proteins, like carbohydrates, in order to, just to say, a more realistic model, which will increase the complexity of our simulation because we need to define all the atomic parameters for all the new molecules that we consider in this kind of system. And the most important step is the last one. Of course, we have started our simulations with triallose because triallose is the classic seroprotectant. It's a molecule that has been studied for these purposes along this last year. But our objective, and one of the objectives of the DryNet project, is to screen a new kind of seroprotectant in which we are going to model this kind of materials, for example, late embryogenesis abundant peptides, new kind of seroprotectant, which will be screened using quantum chemistry methods in order to obtain the atomic parameters, and they will be put in contact with these model membranes in order to see how the structure changes with the reference system, which is triallose, which is our reference seroprotectant, in comparison with this new family of seroprotectant, all of them in silico. So we will be able to check a collection of seroprotectant, a collection of new seroprotectants, which will be designed from the corresponding proteins, and its interaction with the membrane, which is completely new. There is no information at the molecular level of this kind of system. You may see you may find in the literature some studies, some theoretical studies considering interaction with model membranes, with model proteins, using previous form files. Our results use a new parameterization of the form files, which we've been able to model a more realistic model, but these kind of systems are completely absent on the literature. So we don't know how we have some ideas about the behavior of this kind of seroprotectant, which are used by many living organisms, but we don't know what's happening at the molecular level. We don't know its structure, we don't know how they change, how they interact with the lipid membranes, and how the lipid structure can be changed by the presence of a collection of this kind of materials as a function of the, again, concentration, pressure, and temperature. So these are our theoretical efforts, which are, as I have said, at the bottom of the scale. We are modeling atomistic level studies, which will carry out to engineering level studies, to biological studies. So we are analyzing what's happening at atomic level. So that's our effort that I hope may be useful for doing good studies at a higher level. Okay, thank you for your attention.
Thank you very much, Santiago, for really this brainstorming, analytical and theoretical approach. Really very, very interesting. Are there any questions for the audience? Yes, of course, sure, Wim as the first one.
Yes, thank you. This is important work. I think that it will give some interesting results. What do you need as input actually for your model? For example, a lot is known from the MTC, the phase transition temperature, etc.
No,
and also we know if you dry BMPC, the phase transition temperature shifts to that temperature, and with sugars it goes the other direction. Do you need this as an input?
No, of course, it's good for us to have some information about the phase transition, experimental phase transition, because now we have to scan the whole phase diagram, which is very time consuming. But our simulation starts from scratch. So we have this model for this lipid, this model for this molecule, and we are able to predict, in principle, if our model is good, all the properties, how they permeate, how they interact, the phase changes.
So you can also derive the phase transition temperature of derived lipids?
Yeah. Okay, we can predict it. In fact, we have made some tests with our new 4.5. We have do some tests about the prediction of the phase diagram in comparison with experimental results in case they are available. But our approach is purely predictive.
What I see as a challenge in this project is at some point you get a phase change at low water content. So you get a phase change of your trehalose, it will turn into a glassy state. So your molecular motion comes to a standstill. How do you implement this?
We are not sure because we have not in this stage. So we are sweeping some initial concentration range, but this is very important because there is no information about the behavior in this region. So it will be very difficult to model this kind of simulation for this concentration range. So this is, I think, is our most important problem for along the following months. We will try to fix it. Trying to describe the physics more accurately at the interaction, but I'm not sure how it will work. I have to check the performance of the different files for this kind of region. But to be sincere, I don't know how they will behave. We are doing a quick screen of the launch intermediate and low concentration, and let's see what happens when we go to the smaller water concentration, to the lower water concentration. In order to obtain what we're going to see is what's happening, how they are bonded to the interface, and which is the structure of this region in terms of the. But it's not easy to be sincere.
Okay.
One short question. But I was just interested in what you showed. Your area per lipid increases with trehalose. I thought that was an interesting finding.
Yeah.
That would support preferential exclusion.
Yeah.
Is it correct?
Yeah.
So
I think
preferential hydration.
We started the simulation with the idea of water replacement. So we thought this would be but this result was not surprising. So not surprising. So validating the opposite model.
Actually supporting this. So
yeah.
For a long time, the biolayer stays preferentially hydrated,
yeah.
and only at the very last point.
Yeah. So we have previous experience with modeling different behaviors of water-like system, and we have in mind that maybe water replacement could be more physically possible. But the results point to the opposite mechanism. So that's okay. So we change our mind, but we are seeing what's happening. Why? So how is the behavior at the interface, even going to this low concentration region for coming simulation? So,
okay. More questions? Yes, Professor Cincotti.
That was very interesting. I didn't get one thing. You use molecular dynamic simulation, force fields, which means that you need a function for the potential to understand how is a force, the gradient of the potential. But I read that for the trials, we use ab initio model, which is different from force field. Is it correct?
Yeah.
I mean, it's even as lower case. I mean, lower simulation. Is it, I mean, as I understand, molecular dynamic simulation.
So let me show you. So
yeah.
In this case, we are describing this initial for file. So
yeah, ab initio calculations for trials.
This one. So what we're trying to obtain is a realistic parameterization of the full file. You check the literature, you can find different parameterization for this kind of molecules. So in our experience, previous experience and the comparison of the previous model, they are not very realistic. So
you use ab initio to have it?
We do ab initio, yeah, of course. As I have mentioned, when you do molecular modeling, when you do something like this, you have two options mainly, or using the, let's say, available for files, something that in biophysics is, this is our charm, is our pivotal for file, everybody use it, so different parameterization, use it for proteins, for DNA, for whatever you have in mind, but it's very general for file. It has been parameterized for general molecules, so when you study some kind of system, it works. But this is a very difficult phenomena to describe. So we need to have a good, and I repeat, good, for file, for describing what's happening. Mainly we need to describe the interaction between mainly the head groups of the lipids and the water and the seroprotectant molecules very accurately, in order to see if lipid chains, if acyl chains collapse or not collapse, go from gel to liquid light or not.
And you use ab initio calculation to do this?
Yeah, how we do it? We use
okay, I got it.
So,
I know about ab initio.
So what we do is maintaining the structure of the for file. For the people who is not expert in this file, need to have some classical mechanic method that need to have in every molecule the charge of the atom. Every of these atoms has an atomic charge, positive, negative, whatever. You need to describe all the bonds. You have one bond between two atoms, and bonds, of course, are not a static model. They are moving. So you need to describe the force. Describing that model, you have angles between three atoms that are opening and closing, and you have dihedrals joining four atoms that are also opening and closing. So you need to have all these parameters for all the atoms, all the bonds, all the angles, all the dihedrals, and an additional parameter that is called Lennard-Jones parameters, who describe non-bonded interaction, which are mainly two parameters per atom. So you may have 1,000 parameters for each molecule. So what we do is we take one molecule like this, or like this, and we carry out on it what we call quantum chemistry ab initio calculation. This is not classical mechanics, it's quantum chemistry. So we take this structure, we optimize with different methods, we find the most stable structure using quantum chemistry method, an approach that we call density functional theory, that is something more simplified but very time consuming. And we obtain the charge of the atom, the force constant for each molecule. But this is not simple, because quantum chemistry can be applied to a system going from 2 atoms to 1 million atoms, in theory. But the real behavior of this system is that if you want to model a molecule using quantum chemistry method, even with DFT approach, you can go further of 300, 400 atoms. If you want to. The method is possible, you can apply to 1 million atoms. But it will take years to do it. So what we do is use ab initio predictions. We have to model this kind of molecule that can take weeks. So it's not just putting this into a program and obtaining the result in hours. No. To model this molecule can take even weeks. And with this we obtain all the parameters, if needed, or not. Or we can use the previous one. For the force field. And these parameters for quantum chemistry method fit the molecular dynamics. If we obtain a good description of these parameters, the force field is good enough, so the physical behavior of the system is good enough. So if we use, unrealistic charts, bonding parameters unrealistic, so the molecules may collapse or not, but that's not the physical real behavior of the membrane. So that is the fault of our model. So this is the key. So this is the most important. So ND simulations are as good as our force field is. So we can develop a model, but if not good, we are not describing what's happening in the real system.
Excellent. So I will interrupt you. Thank you very much for the brainstorming. Thanks very much, Santiago. And I will invite the next speakers, which are from the local group of DryNet. The first one is Marta Cernik. She will talk about our latest experiments of the effects of layer proteins on protection of cells during dehydration.
There is more than the 10 million of the biological samples, like cell lines or the cells for the cell transplant therapy, or some gametes, or for assisted reproduction technology. Or there are also many samples of the endangered or not endangered animal species which are frozen. And they are stored in the frozen. They are stored in the liquid nitrogen for the long period of time. The storage in the liquid nitrogen, as you know, the technique is extremely easy. It is always used in the laboratory of the biological laboratories. Technique is extremely easy, but the storage, long-term storage, first of all, it is expensive. Then it needs also special equipment to store samples in the liquid nitrogen. The liquid nitrogen can be dangerous for the operator. And also the frozen samples can be freeze with the contamination. We can contaminate them and we can freeze them after use. After 10 years of the storage, we can throw them and we can be surprised that they are not anymore able to be used. And another problem with the liquid nitrogen storage is our environment, because there are more like 400,000 laboratories all around the world which freeze the cells, which store the biological samples, and every month they use around 200 liters of the liquid nitrogen. And to produce all the liquid nitrogen needed for the store of these biological samples, it's like 400,000 metric tons of the CO2 exposed to our environment. That's why the new strategy which we propose in the DryNet the project, new strategy of the storage of the biological samples is needed. We propose storage of the biological samples in anhydrobiosic stage. In anhydrobiosic, it means in the dry stage without water, which allow to store in room temperature for the long period of time. This technique, the dry storage or lyophilization, is commonly used in the pharmaceutical and the food stuff industry. But we would like to introduce this technique for the storage of the biological samples. Of course, the procedure which is available now for the pharmaceutical and food industry do not allow the storage of live biological samples. That's why we try to discover the protocol to be able to conserve anhydrobiosic stage samples for the live cells. Okay, what is anhydrobiosis? Anhydrobiosis is a kind of dormancy, but more extreme. It's like a zero metabolism. The sample, the cells or the tissue are sleeping. They do not have any metabolism on. Why is so important to study anhydrobiosis? Because the tissue of the cells in of anhydrobiotic organisms are perfectly preserved in the dry states for the several decades of the years at the room temperature. If we will able to discover the mechanism which helps those tissues survive in this stage, we can easily transform these factors into the cells of the tissue which do not have this possibility, and then we can develop the dry preservation protocol. This is what we would like to obtain. This is what is now available in the food industry. We have we have dry coffee. For the storage, we don't need any energy. There is also much less volume. We don't have a huge shelf to conserve those samples. We can store easily in the room temperature, and we can even take the samples at home. And then, after a while, whenever we wanted to use them, we just add the water and we have a product ready. This is what we want to do with in our project. We want to conserve our cells, somatic cells, in the dry stage, and whenever we will need them, just add the water, and we will have live, normal cells. But before proposing any protocols, we have to ask the question whether the life without water is possible. And looking at this table, huge table, the answer is yes, because there are many organisms from the seeds of the plants for the large animal, some bacteria, some fungi, which are able to survive without any drop of the water for the many years. There are some seeds of the plants which are able to survive in the dry stage for the 2000 years, and then they are able to germinate. One of the example, it's one of the largest and the highest animal amount anhydrobiosis. The insect which our Japanese partners works on, and the larva of this insect in the dry stage is able to survive in the very drastic conditions. In the dry stage, life can be frozen without any crop protectants in minus 270 degrees for 77 hours is perfectly good. Can be boiled for the 3 hours in the more than 10 degrees, and then after rehydration is perfectly good. Can be vacuum, can be even fixed for more than 160 hours in the ethanol, and it's perfectly good. And it's only 1 hour after adding drop of the water and become alive as before drying. The Japanese did also another experiment. They sent this dry larva into the space. First of all, they expose into the ship. They just send them into the spaceship for a couple of months. Then they come back and they hydrated the larva was perfectly good. But then they try to expose this larva on the outer space. They prepare some special containers. They put here in the middle the larva, then expose for the 3 years this larva into the outside of the space. And they, after 3 years, they came back to the earth and then dehydrate this larva. This is after rehydration and exposure of the earth larva in dehydrated stage, in the anhydrobiotic stage, and after rehydration needs only 1 hour. After 3 years in the space, need only 1 hour to become alive and normal as before. Another example of the anhydrobiotes, it's a tardigrade. It's an animal very famous a few years ago. Since a few years they are very often in the news as one king of the anhydrobiosis organism, because again he's also able to survive in the dry stage more than 10 years. Can be dry till 1% of the internal water, can be also freeze, can be warm up, can be irritated, and it's perfectly good. It needs only few minutes with the water and become alive. Here you can see the dry stage of the tardigrade, and it needs only few minutes, more than few minutes, around 1 hour to become alive again. And this tardigrade, this small animal, it is not exotic animal like a larva which I'll show you before. It is an animal which live close to us. We live close to us. Our collaborators, Japanese collaborators, which came here for the secondment, they just took small piece of the most close to the hotel, and they found like a 5 or 6 tardigrade. It means they are normal. They are not exotic. They are not specific, and they have these beautiful abilities. Another example of the anhydrobiotic, let's say, organism are the seeds, which are able to survive even more in the anhydrobiotic stage. One of the examples, it's from my home. Actually, I bought a couple of years ago seeds of some herbs, and I didn't have time to put them into the garden. And a few days ago, I just, after 5 years keeping in the drawer, I just put on the top of the paper, and I put some drop of the water, and after the next day, they were able to grow and germinate. More extreme example from the seed, from the plants. It's seeds of the plants, palm, found in the Israel during some archaeological studies. Archaeologists found the seeds of the plants which were in the archaeological place for 2,000 years. And of course, they took the seeds and put into the ground, put some water, and after a few weeks, they observed that the palm were able to germinate it after this long period of the dehydrated, anhydrobiotic stage. Another example, the seeds of the magnolia, also thousands of years without any drop of the water, was able to flower after putting these seeds into the ground. What's the secret of these seeds? The scientists think that the secrets of anhydrobiosis in the seeds are late embryogenesis abundant proteins, in short name Lea proteins. And they thought that they play a crucial role in the desiccation tolerance. Lea protein, the first of all, were discovered in the seeds of the plants, in the cotton seeds, and for the many years they thought that they were present only in the plants. They are accumulate in the last stage of the maturation of the seeds. The Lea proteins accumulate. There are different type of the Lea proteins, and they accumulate when the organism desiccate, and they accumulate in different compartments of the cell. They can localize in the nucleus, they can localize in mitochondria, they can localize and they protect cytoplasm, and they are also Lea which localize in cytoplasm and the nuclear. And they protect other proteins from the aggregation due to desiccation. There is also the many studies which show the synergy of the Lea protein with the trehalose. The latest papers show also that Lea proteins are present not only in the seeds, they were found also in the eukaryotic organism, which can suggest that mammalian cells can be protected with the same mechanism as protect seeds and the dry stage larvae. And in 2002, they were also this paper published in the Nature, where they were able to, for the first time, they isolated 3 Lea proteins from this famous larva. Okay, there are not many papers. This is what we are trying to do during the DryNet project. We just try to express the Lea protein, use those Lea protein for the desiccation of the somatic cells. We thought that if they support plants and the dry larvae, they can also be used for the somatic cells. The first paper which used Lea protein in the somatic cells were published in 2012 in the PNAS. The scientists stably express 2 Lea protein in the hepatoma cells, 2 Lea proteins which are localized in the mitochondria and in the cytoplasm, and additionally they also stably transfect the cells with the TRET1 plasmid, which allow to upload trehalose inside the cells. And then they use, for the desiccation, they use the spin dry technique, which is fast spinning, which remove the water from the cells. And then the cells transfected with the 2 Lea proteins, trehalose and spin dry, were conserved in the 4 degrees for 7 days, and after rehydration, after 7 days of decomposition, they observed that 98% of the cells express Lea were still alive. This technique, it's okay, it's very efficient, but not all laboratories are able to produce. First of all, the cells were genetically transformed, and now all laboratories has a spin dryer to dry the cells. And this is what we propose. We propose a much simple protocol for the drying cells which express Lea protein. What we do on the beginning? On the beginning, we just choose 3 different Lea proteins, which are localized in 3 different cellular organelles. First Lea protein, we call them simply Lea number 1, but it's RAB70, which normally is expressed in ZIA mice. This protein localized in the cytoplasm and nuclear in the cells. Additionally, we clone this layer into the GFAP vector, thanks that we can easily localize this layer in the cells. The second layer protein number 2, which is VCOR 410, normally expressed in Tritium arestivum, and has perimembrane localization. And also this, in this case, we clone into the red fluorescence protein vector for the easier localization. And the third protein, which is normally expressed in Artemia franciscana, which has a mitochondrial localization. And again, here we clone into the BFAP blue fluorescence protein for the easier localization. First thing which we do, we just express this 3-layer protein in the sheep fibroblast. Sheep is our experimental model. We simply transfect our cells with first layer protein, which is layer number 1, GFAP. On the top pictures you can see expression of the layer protein. Here you can see clearly cytoplasmic and nuclear localization. Here it's nucleus and here it's merge. On the bottom I put the picture of the control group. As a control we use transfection with only tag, only GFAP. Here maybe it's not visible perfectly, but we could see a clearly completely different localization of these two proteins. Here you can see the all cells green, here clearly cytoplasmic nuclear localization. Then we confirm expression of the layer protein number 1 by Western blot. We extract cells after 24 and 48 hours post-transfection. We observed that for 24 hours was better and higher expression of the layer protein. The conclusion is that we confirm cytoplasmic actually for the first time, the cytoplasmic and nuclear localization of layer protein number 1. Then the layer protein number 2, I don't know if it's visible, you could see.
Can you put the lights down?
Layer protein number 2, here again on the top, here on the left picture, we can see expression of the layer protein RFAP, which is cytoplasmic nuclear. You can clearly see black nucleus in empty nucleus, which again as a control I use only RFAP tag, which is expression is very similar to the GFAP, which confirm that the cells, that the layer protein localize correctly. And also in this case I confirm expression of the layer protein in the sheep fibroblast by Western blot. And the last layer protein, the layer number 3, which has a mitochondrial localization. Here you can see clearly mitochondrial localization of the layer protein number 3, which again as a control I use only tag BFAP, which the localization is completely different from the layer protein and is similar to the tags which I showed you before. Just to make sure that the expression it's really mitochondrial, I transfect again the cells with layer number 3, and then I stain those cells with mitotracker, which recognize active mitochondria in the cells, and we can clearly see the merge when we put the merge of the cells that the layer protein co-localize with the mitochondria, which confirm again that the localization of the layer proteins is correct. And again, it was confirmed by Western blot analysis. And then, when we confirm the proper expression of the layer protein, we use those cells, we transfect those cells again, and then we just dry them on air. What we did, we transfect the cells and we resuspend them in the medium containing trehalose. Externally support the cells with the trehalose. We did a small drop, 10 microliter drop of the bottom on the culture dish, and we dry them in the 16 degree for 4 hours, and every hour we control number of the live cells. Here on the graph green you can see cells transfected with the Lea protein number 1, red Lea protein number 2, blue Lea protein number 3, and the gray graph you can see the control cells. After first hour we do not see a huge difference, but starting from the third hour of the air drying, we could notice that the control, it means non-transfected cells, completely disappear, while the Lea protein, which the cells which express Lea protein, around the 40% are still alive, and even after 4 hours of the air drying, they were still alive, while the control, of course, they were not anymore present. And then we noticed during the experiment, we noticed that the cells on the air dry, they are actually sensitive for the changing conditions. And every time when you open, every hour the hood, the conditions change and the number of the cells decrease always more. And then we decided to calculate only after 3rd and 4th hour of the incubation of the air drying, and we noticed that a much higher results in after 4 hours of the air dry, the cells, more than 50% of the Lea expressed cells were still alive, while the control one not expressed or no expressed Lea protein were almost all dead. Then we thought, okay, but if the single Lea protein has this ability of the protective of the cells, we thought it would happen if we transfect the cells with the all 3 Lea protein at the same time. This way all the organelles can be protected even better. And of course we are not able to express in all cells all 3 Lea protein in the same time. But anyway, in this transfection trial, we had mix of the Lea proteins. We had cells which express 3 Lea proteins in the same time. We had cells which express only 2 Lea proteins, and there were also many of cells which express singular Lea proteins. Here you can see some examples just to show you that the cells which express 3 Lea protein at the same time. Here you can see Lea protein number 2, here Lea protein number 1, and Lea protein number 3 in the same cell, and here you can see a merge. Here there is other example of 2 Lea protein expressed in the same cell. You can see Lea protein number 3, Lea protein number 4, Lea protein number 3, which co-localize, which is mitochondrial localization, and they clearly localize with the mito tracker, which is specific for mitochondria. And here you can see a picture of the merge, just to confirm that the localization of this Lea protein. And again, we did the same experiment. We transfect the cells with the 3 Lea proteins. We call them mixed Lea. And then we easily, simply air dry them in the 16 degree in the presence of the trehalose. And how we, it was not surprising that the mixed Lea protein were much higher. They protect cells from the desiccation injury much better. Here, just to compare to the control, it means non-transfected cells. After 1 hour, it is not big difference, but starting from the 2 hours, the mixed cells, mixed Lea cells, more than almost 90% are still perfectly good. And after 4 hours of the air drying, almost all control cells were dead. When the mixed cells, it was around 60% still alive and good. And then compared to the single Lea protein, again, of course, mixed Lea proteins win. Compared to the Lea 1, 2, or the 3, after 1st and the 4th hour, there is a statistic difference between mix and the single Lea protein, which can conclude that the synergy between Lea proteins enhance the desiccation tolerance. And then after desiccation, we rehydrate those cells and we transfer them into the culture, just to check whether those cells are still able to proliferate or how the organelles looks like after dehydration. Actually, this is the results are from yesterday. They are not complete, but just to show you that the cells after desiccation, after 4 hours in the air drying, and then we rehydrate them and they transfer into the culture, and day after we did the proliferation assay using BRDU, And we noticed that the control cells, which were desiccated, it was like a 0.01% cells which attach and were proliferate, while the LEA mix, LEA BFAP, it means the LEA which express in the mitochondria, were compared to the control, it means non-desiccated cells. It means they are perfectly able to proliferate after desiccation. When the control, it means the LEA protect from the desiccation and do not affect on the proliferation. Then we wanted to check whether the desiccation effect of the mitochondria. One of our protein, as I told you, is expressed and protect the mitochondria. And we wanted to check whether desiccation effect on the mitochondrial structure localization. Here on the picture on the top, you can see the control dried. It means control dried. It means dried cells without any LEA expression. Here in the middle, control. It means non-dry cells, normal culture cells. On the bottom, you can see LEA protein, which express LEA protein 3, which localize in the mitochondria. On the top here, on the left, we stained cells with the mitotracker, which recognize active mitochondria. And in the control cells, you can clearly see that the mitochondria are fragmented, at the degenerated, and also the localization of the mitochondria, it is all around the cells, not as control one close to the nucleus. Control cells, you can clearly see that they create like a line, they fuse between each other, and they are localized close to the nucleus. Similar, sorry, this was the control, but actually control and the LEA protein are very similar, which means that the LEA protein, LEA, which localize in the mitochondria, support mitochondria from the desiccation injury. Just a few very fast conclusion. Just to conclude, we can clearly see that the LEA proteins are very promising candidates as the xeroprotectants. They protect cells from the desiccation injury, which helps to survive the desiccation stage. And also we noticed, of course, it was not surprising that the synergy between LEA proteins even more enhanced the desiccation tolerance of the somatic cells. Thank you so much. This is our group, the DryNet group from University of the Teramo.
Thank you very much, Marta, for the exciting results. Every time I see this picture, I jump because they are so beautiful and so convincing, actually. Thanks a lot. Please, I will take yes. Wim?
Yes, so these are some exciting results, I think, showing that your proteins actually increase desiccation tool. I want to know a little bit more about the experimental, how you did it actually. So I missed so you dried at 60% relative humidity, so you have sort of a slow dehydration phase. What was the sample volume? How did you do that? And what was the container? How did you dry it?
Actually, it was very simple, very homemade and handmade. We just took the culture dish, plastic culture dish, petri dish, opened them. We just dropped the samples.
What was the volume?
10 microliter.
10 microliter. Okay.
Yes, 10 microliter of the drops, and then just put into the, it's called the oven, I don't know, the fridge, 16 degree.
Yeah.
And we left for the
16 degrees Celsius, right?
16 degrees Celsius.
That's fairly cool. Yeah, it would be interesting to find out what water contents are at after 1 hour, 2 hours.
This is what we are
10
actually.
microliter is very small to do it, so you could think about doing some parallel studies where you can determine water content. So you can match up, okay, after 4 hours my water contents, they're probably not completely dry, I estimate, but
This actually what is our next step. This is what we are planning to do
Yeah.
in the further, because we wanted to, of course, we wanted to know.
Yeah, definitely the water crisis that is induced in the other cells, untreated cells, is almost fatal. They almost all die, so there is a clear protection. Yes, we might tell it's a short time, 4 hours, but still, they're still alive, thrive well, the other one permanently compromised.
Actually, it's also our next step, because they were not controlled condition. They were like dry on the bench. Our next step, we would like to know a little bit more. We just wanted to dry them in the more controlled condition, maybe with the lower humidity atmosphere, and maybe in the different temperature. We use 16 degree because actually it was the unique place where there was not a huge difference of the atmospheric conditions. That's why we transferred it to 16 degree. But anyway, the results show that this is the future. Okay. Yeah, but the results in a way show that something is going on. The Lea helps somehow.
Yeah. More questions? No questions, so I think we'll skip. We will discuss every day with Marta, so I will ask them something later. Can I invite the last picture? Okay, Dulce del Fundo, our youngest postdoc in the group. Luca, which will tell us his recent work done on lyophilized or dry spermatozoa and ICSI. Enjoy the talk.
So, thank you, Professor, for the introduction. Good morning to everybody. So, first of all, what is a freeze-dried product? I think that everybody in this room touched the freeze-dried product. I think about antibiotic, vaccines, or just coffee and tea. So freeze-dried product is a dry product, is a powder, and if you underwater, you can restabilize the biological function. But if we speak about spermatozoa, how Marta said before me, the total of biobanking of sperm in the world use the liquid nitrogen to cryopreserve spermatozoa. But liquid nitrogen does a bad thing from its birth to its death. Indeed, for the production of liquid nitrogen, there is a strong carbon footprinting. So the production of liquid nitrogen increases the pollution of the world. And also the use of liquid nitrogen is dangerous for the operator, because you know that liquid nitrogen have a very, very low temperature, and if you touch, you can burn your skin. So also it's my personal aim to remove the liquid nitrogen from the earth, because every time I play with liquid nitrogen, I burn my finger. And if we move on the specific use of liquid nitrogen, the biobanking need to use a specific room to store the sample. I mean air conditioned circulation, from removed out to put out the vapor of liquid nitrogen and put inside oxygen. And also the liquid nitrogen, as is shown by this picture, have a very fast evaporation. So you need to produce again liquid nitrogen. So, and the problem starts another time. And the Earth is the only one that pays the bill for everybody. So to switch on a dry cryobanking, in my opinion, so in our opinion, I think that for this project, this demo, everybody, is a good solution to remove the liquid nitrogen for biobanking. Okay, so what is the point until today from the freeze-dried sperm? The first strong milestone was provided in 1998 by two big scientists. The first is Teruhiko Wakayama, and the second is Yanachimaki. For the first time, they proved that mouse epididymal freeze-dried spermatozoa can give a live offspring. And after this, there is a working rabbit, but the rabbit is not very live offspring, because unfortunately the rabbit died during a dystocic delivery. And quite obviously, after mouse, we have a rat, also a live offspring of rat from freeze-dried, ejaculated, and also not ejaculated spermatozoa. And from the rat we have the first fall. I put the horse into a quotation mark, because the author of this work for the ICSI, use, yes, freeze-dried spermatozoa, but use also a sperm extract. So you know that in sperm extract, maybe there is a still DNA or sperm head, but the main issue is that the horse that provided the sperm extract and the horse that provided the sperm for freeze-drying is the same. So we have to trust if the folate born is from the treated horse. And the last one is also provided by the first author, Wakayama. I call this paper Mice from Space because so the travel space and also the creation of another Earth, another planet is not just a fantasy movie from in the cinema or romance. It's a concrete, a really problem issue from this side that work in this field. So this the author of this work freeze-dried a sperm in the Earth, of course. Take a shot, put the sample in a shuttle, and the sample was shipped in an international space station, and they stay for 9 months. And after 9 months, the sample go back to the Earth, and it was performed by ICSI. And from this ICSI, we have a live offspring. So we prove that you know that in the space there is not the ionosphere to protect us from the X-ray. There is only the metal panel from the building of the space station, and the dry sample, in this case the dry spermatozoa, can survive from the X-ray from the space and can do a live offspring. Another point, a good point for this paper, that for the first time the author not give only the offspring, but use also a new generation sequencing for check there is a point mutation in the live offspring, in the treat sample, I mean, from the control. The control is from used only in the Earth. Okay, so what is our work here in Teramo? In our team, we use the sheep model, so ram spermatozoa. We have a little group from a few kilometers from Teramo, from here, sorry. So we take the sperm, and from a liquid matrix we use a freeze dryer in our laboratory, and for a liquid matrix we move on a dry matrix. And from a dry matrix we just put water inside the vial. I sit in front of the manipulator, I perform the ICSI, and if everything is good, 7 days after we have a blastocyst, like in this picture. So, the first evaluation was after the redatation, of course. So this picture is our sample after redatation. This is the bright field. This is the propimidite for the anidite, and this is the merge. So, of course, the first observation proved that the sperm is not motile. So, until now, the sperm are not motile. We need eggs to perform a fertilization. And but in my opinion, a good point is that the sperm preserves the total body, because if you read the paper, also the paper that I showed before, the sperm after redatation is not very integrally. You have a lot of tail-cutted, so aviated sperm, and so in my opinion, it means that the protocol that we use is not too much mechanical stressful for our sample. Okay, another aspect that we check, you know that after the fertilization, there is a communication from the sperm to the eggs that say, okay, I'm here, we have to restart the meiotic cycle to reprogram the head of the sperm, and also to restart the meiotic cycle of the eggs. And usually with fresh or frozen spermatozoa, if you use a ICSI, and of course, if you have a good sample, you don't need to do a chemical activation. So the sperm do everything by themselves. But we found that in our sample, A is not activated, A is activated. We see that there is a difference. So, how's the 24 hours we check the cleavage of the embryo. So, and we see that the oocyte activated after the ICSI have the highest percentage of 2-cell stage embryo than the non-activated oocyte. And for the blastocyst stage, the oocytes that are not activated not reach the blastocyst stage, but the oocyte that activated after ICSI, we have a blastocyst. So this picture is another proof of the chemical activation. The A picture is the oocyte activated, and the B picture is the oocyte not activated. So break field, protein for the DNA dye and the merge, also the same also in the B picture. We see that in the oocyte activated, we have the formation of the true pronucleus. So the oocyte open and remodel the compact, the sperm head, and also restart the cycle. But if we see that the oocytes that are not activated, the sperm head is still compact, and also the X is still blocked in the metaphase 2 phase. Okay, so this is a work that the major work is performed by my colleagues, Dr. Anzalone. We applied the freeze-dry for the endangered species. So this is Diego, is one of the last ram with Pagliarora breed. Pagliarora breed is an endangered breed in a local breed, in a Abruzzo breed. And Dr. Sanzalone, in a previous work, established a liquid nitrogen biobanking of the sperm of these endangered species. And so now we try to switch from a liquid nitrogen biobanking to a dry biobanking. So this is the output, so the outcome of comment?
Diego is dead.
Diego is dead, yes. Yes, but there is the son now. Donino. The son is still alive, yeah. Okay, so this is the blastocyst produced by frozen sperm, and this is the blastocyst produced by freeze-dry sperm. So we prove that we can switch from a liquid nitrogen biobanking to a dry biobanking for endangered species. Okay, so as I said before, the first milestone was provided by epididymal spermatozoa. So, in my opinion, I'm a PhD student, so when I started to work about 3 years ago, so I started to work with epididymal spermatozoa because I think, okay, so if the first result is provided by epididymal spermatozoa, in my opinion, maybe I can start from this point for my experiment. Also, another thing, if we translate in human scientists, I mean some case of male infertility, for example, azoospermia. This is the case that the patient have not ejaculated semen, but you have to take the epididymal spermatozoa. So we can try to extend the field of freeze-dry spermatozoa in epididymal spermatozoa in large animals that are more closer in the human model. So we did an experiment. The collection of semen and the freeze-dry of semen was done by our colleague, Dr. Salgusti, in Berlin, and he shipped to us the sample by a normal air purity mail, so also in the aim of environmental friendly. And in Teramo we did the experiment.
With a pigeon.
Pigeon, yeah.
Truly.
Okay, so in this work we are focused also in the DNA fragmentation of the sperm after drying, and we check the two different degrees of fragmentation, the single stem break and the double stem break, because the oocyte, you know, have a very big quality to repair the DNA, to DNA repair, but there is also a limit in the SBS level. So if there are a lot of the SBS level, the oocyte can do a very good work. So the experiment we use is the two-tailed comet assay to see how is the SBS and SBS degree. So the shadow comet, it means the SBS, and the green clouds is the DSBS, and this is also the sperm chromatin dispersion. The first two sperm is fresh and frozen sperm, and the other sperm is a freeze-dried sperm in different degree of SBS break. this is the normal filter, black and white, and this is the electronic filter to align the level of the SBS in blue. Okay, so if we focus on the table, we see that, so we use 4 RAM for the experiment, but this RAM have a different degree of DNA breaks. The RAM 2 and the RAM 4 have the single more level normal DNA. Okay, when I do after the ICSI, so I think that the outcome of epidemial spermatozoa was the same of ejaculate spermatozoa, but it's not happened. My thinking is that maybe the epidemial spermatozoa are not very matured to fertilize oocyte. But the interesting result, as I said before, only 2 RAM reach the blastocyst stage, and this is maybe, in my guess, correlated to the level of DNA fragmentation. Indeed, only the RAM 2 and 4 reach the blastocyst stage. And this is the blastocyst that we produced from this RAM. This is blastocyst from RAM 2, blastocyst from RAM 4, and this is the control of ejaculated freeze-dried sperm. So if you compare also the morphology, it's very close to the control. And this is the control for X quality parthenogenetic embryo. Okay, so we just now work only in the ICSI, and that's it. We also think about how to improve the freeze-dried protocol in sperm. Last autumn, I spent 1 month in NIAS Institute, placed in Tsukuba, Japan, in the aim of DryNet project. And in this occasion, I had the opportunity to speak about a very good science in this field. Also, I meet another partner, Dr. Religious, and everybody have a good brainstorming with freeze-dry. And from this experience, I learned to focus in the readaptation phase. Why? What is the thing? So, ideologically, the sublimation removes the water. So, only the salt are still attached in the sample. We only just add water to readaptate. But I think it's not just this. Because maybe the water is too much, or maybe the process is too fast, and we have for the first time osmotic stress, but the second step is a mechanical stress. I think the mechanical step destroys everything. So, I think that the dry sample is like a sponge. So, they can take the water from the humidity. Maybe they can take the water just as you want from the humidity. So, why not readaptate in a humidity chamber very slowly? So, I create this very simple experiment. I take a big beaker, I put inside a little beaker with water at 37 degrees, distilled water. I put also the sample that produced the RAM, and I put in the oven at 37 degrees for 2 hours, and then I performed the ICSI. And this is the data. These are very fresh data. I performed the ICSI last week, so I can only check the cleavage. But the result for me is interesting so far now, because the sperm readaptated in humidity chamber HC increased the level of 2-cell stage, so the 10% more the normal readaptation, and this is the embryo that we produced from this experiment. Okay, so we are able to produce blastocysts from freeze-dry epithelial or ejaculate sperm. What is the next point now? This is my next experimental drawing. So, I was said before, only Wakayama with the mouse, sheep, did a comparison with the new generation sequencing, because until now, if you check in PubMed or bibliography, there is nothing about new generation sequencing to prove if the dried animal or dried sperm or dried cell, everything dried, have some mutation, some methylation defect. Nothing is about this. We have not information about this. So, in my opinion, we work in a large animal, So it's a good thing to be sure that the semen that maybe you put tomorrow in a sheep is good to give a lamb. So the experiment row is very easy, very simple. We take the blastoids that we can produce very easy in our laboratory for freeze-dry sperm. We take blastoids by IVF technique, normal nuclear fertilization. We do an outgrow, and then we establish a cell line. And from this cell line, we can compare with global methyl-homotraxyltome or point mutation, everything as you want, and we can check how much closer is this sample to this sample. And of course, the last word is from Dry to Life. I call this picture because so the last word is we can have life from this dry sperm. So we take our blastocysts, we did an embryo transfer, and maybe if you are lucky, 5 months after we have a lump. So yeah, thank you for the attention.
Okay. Thank you very much, Luca. I can guarantee that these data are really fresh because they're working on the laboratory just in a couple of days ago, yesterday, 2 days before yesterday. So really, they are work ongoing. Thank you very much. Questions from the audience? Martha, please.
At the end of the freeze drying process, what do you have above these samples?
Where we store it, you mean?
Bio.
Okay, so ideologically you can store in the room temperature, like just you can leave your desk because it's vacuum, it's dried, everything is okay.
Vacuum in the bio?
Yes, of course. We can do a vacuum in our sample. But if you read the paper in freeze dry, so also the paper from Wakayama and Yanagimaki, the problem now is proposed by the engineer and the physics partner is that there are some water still attached in the sample. So the vacuum is not enough to preserve until now the sample. And this author suggests to leave the sample in a fridge or maybe in the dark to go slow the degradation of the sample. Until now we check both room temperature and dark. Yeah.
Did you conduct accelerated aging studies?
Sorry?
Did you conduct studies to know how much time this will
we are working now, so because I'm fresh knowledge for this field.
Like
So
very different results with the DNA fragmentation, for example.
yeah.
This time.
Maybe yes, it's my guess. Maybe because so the problem is the water. So we have to remove the water.
But sometimes you have good results just right after freeze drying.
Yeah.
But it doesn't last.
Yes, this is not maintained during the time. Yes, this is the problem. I think that the main issue is the water. So if we have, if we can prepare a sample with the correct quantity of water, maybe we can preserve the sample for a long time.
And in the environment too, that's why I imagine.
Yeah, so there is different way that we can work. Yeah, the water is one of the majority, in my opinion.
Thank you very much. Wim?
Yeah, so very fascinating talk. Yeah, one comment first. So we've seen actually this is interesting, this rehydration. That's good that you pay attention to this. We've seen this also with platelets, freeze-dried platelets. If you rehydrate them from the vapor phase, if you plunge the water directly, you get balloon cells, and you can prevent that by this gradual rehydration. That's an interesting finding. You have to be very careful not to do it too long because that's also not good. So how did you, I missed a little bit your freeze-drying details. What did you use in your freeze-drying formulation? How did you freeze the cells? And what were your freeze-drying parameters?
So the protocol that we use now is the same of Wakayama or the last paper. So it's very easy.
There's no sugar there?
No sugar, it's just AGT.
Good.
Yeah, I know, yeah. So we just use a DTA to, and that's it. And we put in freeze dry and we dry the sample.
Maybe it's a suggestion to implement sugar.
Yes, of course.
We see that it
Yes, yes. Indeed, my colleague Dr. Sanzalone work in the freezing process, and me I concentrate in the relatation process.
Is it controlled freeze drying in terms of, or is this just, can you control the shelf vacuum pressure or no?
Our freeze dryer is not like your freeze dryer that you show your picture. You cannot manage very good the degree. Yes, yes. Maybe for a very sensible experiment, we need a machine like you.
For small samples, it's okay.
Yes, yes, yes. But this is a project we speak about, George, in Japan. Yes, yeah, this is a problem. Thank you.
More questions? Students? If there are more questions, I thank all the speakers. Actually, we will finish our workshop right in time, so just 5 minutes, longer than what was planned. So thank you very much. I've learned a lot. Thanks to the students also. Thanks for coming, even if it's a kind of empty phase in the university. Thank you very much for joining us. Okay.
What? Lunch? Yes. We are going for lunch. Quindi ritorniamo,